So welcome to everyone to another beautiful day at the IFT IBS-MultiDark workshop, 5th edition. So today, this morning, we're going to have in the mix 3 institutions, each on a different continent. So you see the power of this conference already. And our first speaker is going to be Irene Valenzuela from Harvard University, who is going to tell us about sharpening the Swampland conjectures with less symmetry. So please go ahead.
Okay, thank you very much, Fernando. And also thank you for the invitation to give a talk in this workshop. So I'm going to talk about some recent work with Fernando here, Stefano Lanza, and Luca Martucci that I will combine with previous works and with several things that I've been thinking about. So, as Eran very nicely introduced the other day, my talk is going to be about Swampland, which means that I'm going to be talking about some Swampland conjectures that propose new criteria that any effective field theory must satisfy to be consistent with quantum gravity. From a phenomenological point of view, this is interesting because these new conjectures can provide new guiding principles to construct vision standard models that maybe describe dark matter candidates and so on. And also, as Edu remarked, they have the potential to give a new insight into the naturalness issues that we observe in our universe. So there has been a lot of activity in the last years about these conjectures. Here is a map of different conjectures and their relations. And what I'm going to do is I'm going to focus on 3 of them. And since this is a workshop focused on phenomenology and the dark sector of our universe, I'm gonna try as much as possible to go slowly and also to focus on those questions that I think can be important for phenomenology. So one of the things I will show you is that something that is very powerful and I find very exciting is that we are discovering more and more relations between these conjectures, which might hint to some underlying principle behind all these conjectures that we are yet to discover. Okay, so since Eran and Edu and many speakers already introduced some of these conjectures the other day, I'm not gonna spend a lot of time on the details, but I'm gonna just at least briefly describe what is the formulation of the conjectures in case someone was not there. And of course, you can ask me any questions if you have. So the Swampland distance conjecture tells us that there is an infinite tower of states that is becoming exponentially light at large field distances. When some scalar field becomes very large, then the tower becomes exponentially light in terms of the proper field distance, okay, the geodesic distance in this modular space. The weak gravity conjecture tells us that if we have a gauge field, then we must have also an electrically charged state with a charge to mass ratio bigger than the value of the extremal black hole. That is an order 1 factor. And the no de Sitter, so I'm going to focus on some version of this conjecture in the sense that there is a universal asymptotic behavior of the potential at large distances. So again, when we make a scalar field very large, in addition to having some tower of states, there is also some particular behavior of the scalar potential that has some runaway towards infinity. Okay, so the questions that I think are relevant for phenomenology and are open questions for these conjectures is, well, first, there is, I think in the last years, we have made a lot of progress testing these conjectures in string theory, but mainly all the evidence comes from setups in which we have extended supersymmetry. So n equals 2 or n equals 4 in 4 dimensions. And one very important question is what happens when we lower supersymmetry, right? When we have n equals 1, and then maybe it's just broken spontaneously, or when we don't have supersymmetry at all. So what happens with the conjectures there? Because if we want to apply this to phenomenology, we need to understand this scenario. And the other question is that, as you can notice, there are many order 1 factors in this conjecture. So, for example, the tower decays exponentially, but the rate of the tower, this lambda, is some unfixed order 1 factor. And the same with the behavior of the scalar potential. So the slope has to behave as the potential, but this C constant is also an order 1 factor. And the question is whether we can be more precise about these values, right? Because then if we want to use it for phenomenology, again, it's very important what these order 1 factors are and whether we can compute them. In the weak gravity conjecture, there is also an order 1 factor. But the thing is that this is, we know what is related is given by the extremality value of the extremality factor of the black holes. So it's something that we can compute within the EFT. So we would like to get something similar for these other two. So these are the questions that I'm going to translate. Well, of course, I don't have a complete answer for them, but I will describe what is the status and the state of the art regarding these questions for the conjectures. Okay, so this is the outline. So I will start, since we want to lower supersymmetry, everything I'm going to say is going to be about n equals 1. So I'm not going to talk anymore about n equals 2. And I'm going to consider that we have 4 supercharges only in 4 dimensions. And then we'll see where the tower of states come from, because now, unlike in n equals 2, it cannot come from a tower of BPS particles, because we don't have BPS particles in 4 dimensions with n equals 1, but we have BPS strings. So I will describe some proposal in which it always comes from BPS, from excitations of the strings. And then very briefly discuss what happens if we have a potential. Then we will discuss if there is indeed always this runaway of the potential at infinite distance, and how also we can understand it in terms of membranes. And at the end, I will give a summary of what is the conclusion regarding all these order 1 factors and how we can indeed determine these factors in terms of extremality and the asymptotic geometry. Okay, so let's start with the first part. So consider that we have a 4-dimensional n equals 1 effective field theory. Okay, so we have some kinetic terms for the scalar fields and we have some scalar potential. Now, I'm gonna give you first what is the summary of all the picture that we propose, and then I will explain in more detail some of the steps. So the idea is that at large distances, when phi goes to infinity, there is an approximate axionic strip symmetry that will emerge. Okay, so we will be able to decompose phi on some axion and some axion, that is some periodic scalar. And when this happens, it's possible to dualize these axions to 2-form gauge fields. Okay, while the axions then get dualized to some dual axions. And then the idea is that every time we go to these large field distances, indeed the distance conjecture is satisfied because there is a weakly coupled axionic string that is becoming tensionless. Okay, in terms of this proper field distance. This string is charged under this B2 2-form gauge field that is dual to the axion. Now, I think something very interesting is that if we make the string to satisfy the weak gravity conjecture, I will show you that then the distance conjecture is automatic, so that indeed the tension of this string behaves exponentially in terms of the proper field distance. So one can derive the distance conjecture from this. Okay, so this is sort of the overall picture. Let me explain you how this result comes. Okay. So we have, consider that we have some strings, some BPS strings. So we are going to consider half BPS strings. Because of supersymmetry, the tension and the charge of the strings is completely determined. We can determine the tension in terms of the scalars, okay, in my theory, the dual axions, and the charge, the gauge kinetic functions, so the gauge couplings, are just given by the field metric. Okay, so the field metric is parameterized by the gauge couplings of the 2-form gauge fields. One can show that this tension and this charge satisfies of cell this condition, which can be understood as a no-force condition. And the idea now is that, well, These strings have a very low codimension. Okay, so this implies this generates a very strong back reaction in my geometry that I cannot neglect, and this back reaction is what plays the important role in all this story, the protagonist. And so what we do is to find some solution for these strings, okay, or the equation of motion. This was already done in this very old paper. And if you try to find a solution with this string, you see that the back reaction of the string induces a flow on the scalars. So the axions are driven to infinite distance at the core of the string, while the axion undergoes a monodromy around the string. Okay, so this is the solution. Now, since we can determine the tension in terms of the scalars, we can plug back this back reaction and get how the tension changes. So here we are going to take some approach that was already used for some people, in particular Polchinski, in which we can interpret this back reaction and the geometry in terms of an RG flow. So the same way that it tells you how the tension behaves in terms of R, so the distance to the string, the same profile tells you how the tension behaves in terms of the cutoff of the theory. So if you have a string in a given effective field theory with a given cutoff lambda, if you change the cutoff, this tension is going to change in this way, where I am identifying the distance with the inverse of the cutoff. So we have, let me also mention, I will explain later, but the charge of these strings goes to 0, so they are weakly coupled. And the idea is that then we have two different pictures. So one is that we have the string and we approach the string, and we have how the tension changes with the distance, but the other is that we have a string in a given effective field theory and we change the cutoff. And both are described by the same profile. And then in this second picture, indeed, can be related to how the tension of the string is changing if we move in the modular space. So instead of thinking that we are changing the cutoff, we can think that we are changing the scalars. So this is also describing some particular trajectory in the modular space. And this profile also tells us how the tension of the string is changing when we send the scalars to infinity, when we approach these infinite distance limits. Okay. So in particular, if we send lambda to 0, so we go away from the string, the tension goes to infinity. So there's a moment in which we enter into a strong coupling regime. That's why the strong back reaction, there's a strong back reaction from the string. But more important, if we try to approach the string, or in other words, in the other picture, we send the cutoff to infinity, the tension is going to go to 0, right? If lambda goes to infinity. Which means that there is a moment in which the effective field theory is also going to break down. Okay, so you can the cutoff, there is a maximum value for the cutoff of the theory that is consistent, because in the moment in which the tension becomes lower than this cutoff, I mean, the effective field theory doesn't make sense anymore. I mean, you get sensitive to the degrees of freedom of the string, and you have to change the effective field theory. So this smells a lot like the distance conjecture, right? That you have new degrees of freedom that appear and the effective field theory breaks down. Okay, so just because of this RG flow and this back reaction, these weakly coupled axionate strings are associated to infinite field distance limits. What we were also studying is that this correlation is more powerful because it might also be a one-to-one correspondence, in the sense that for every infinite field distance limit in 4-dimensional n equals 1 effective field theories, we can identify some weakly coupled axionate string. And this statement, this one-to-one correspondence, is what we give it a name, and we call it the distant axionic string conjecture. So that all infinite distance limits of a 4D IFT can be realized as an RG flow endpoint of a fundamental axionic string. And the evidence comes from studying different examples in string theory. So all the examples that we have checked so far of compactifications to 4-dimensional n equals 1 always have this string. So this will appear in an upcoming paper. And there is a story, a very nice story that appears in higher dimensional modular spaces, because what I told you about is like the easy case, But in general, not any BPS string will be weakly coupled. Only a subcon of all the string charges will be weakly coupled. And only those ones are related to strings becoming tensionless at infinite distance, while the others, the instanton effects become important, they become strongly coupled and might be related to strings that become tensionless at finite distance. So this is a rich study that will appear in this paper, and I'm gonna skip, I'm not gonna say more things at the moment, but I just wanted to give you a glimpse of what is behind.
Excuse me?
Okay. Yes.
Please. So do you mean a critical string here, or do you not care here about the nature of the string?
I'm not clear about the string theory nature of the string. I mean, this is like purely from 4-dimensional n=1 supergravity. It's gonna be weakly coupled. So it will also, I mean, we expect that if you try to compute how many degrees of freedom, the excitation moves, you will get an infinite tower. And then in practice, in many of these examples, it becomes the critical string. But that's something.
But yeah, unless it's a critical string, then you may not know how to quantize it to get an infinite tower. If it's is it not? I guess it's important in your argument to say that this leads to an infinite tower. Right?
Yes. So this is something. Yeah. So as I said, like then going to string theory examples. I mean, sometimes we can really identify with a critical string, and then you could know. I mean, we can use the fact that we know it includes an infinite tower of states. We should go sample by example and see if there is some case in which we cannot identify and we cannot count. I mean, this is like the second step of the work, right? Like one should then spend time trying to check if there is really an infinite tower of states. Here, our expectation is that there will be, because the string becomes weakly coupled, but it's something to study in more detail, yeah, for sure. I mean, I'm not giving more detail because this is from the upcoming paper, so it will depend a lot on all the casuistics of all the examples and so on.
Okay, thank you, thanks.
But yeah, you're right. Okay. So all I wanted to say, just to finish this, is that the ingredients that I gave you are enough already to derive the distance conjecture from these strings. So the idea is that if we have some effective theory with a given cutoff lambda, the modular space that is accessible by the EFT is finite, because, as we say, there is a moment in which if we try to send the cutoff to, if we have a finite cutoff, in the moment in which the tension becomes of the order of the cutoff, the effective theory breaks down. So the bigger the cutoff is, the bigger is the part of the modular space that we can access, so the distances that we can move in this modular space. And we can try to quantify this more. So the distance, the field distance that we traverse in modular space, in the field space, when changing the cutoff, is given by it's going to be the integral of the field metric, but since the field metric is parameterized by the gauge couplings of the 2-4 gauge field, indeed it can be just written as the integral of the charge of the string. Okay, and if we replace, that the charge can be written in this way by using the no force condition that I told you the strings obey and some properties of the RG flow. This distance can be just written this way in terms of the integral of 1 over the charge integrated over the tension. And if we now impose that the string satisfies the weak gravity conjecture, so the charge is bigger than the tension, then this automatically gives that the distance goes as the logarithm of the tension. So since this tension acts as the maximum cutoff of the theory, so the new EFT cutoff that you can have, we indeed recover the distance conjecture, right? Because it's going to decay exponentially in terms of the proper field distance traversed in modular space. So the weak gravity for the strings implies the distance conjecture with a factor that depends on the extremality factor of the solution. So let me remark that here I didn't impose or assume anything about the Keller potential or the geometry or anything like that. I'm just taking a 4-dimensional n=1 perspective, imposing that there is some string. And just because I want the string to be a solution of the equation of motion, I have this RG flow and all these things. So the only thing that I'm really assuming here, I'm only assuming is the weak gravity conjecture. Okay, that the string is satisfying this weak gravity conjecture.
Irene?
Yes.
The trajectory that you choose is a geodesic, or, I mean, well, this is set by the equations of motion. This is what you're saying, right?
Yeah,
Okay.
exactly. So it's the trajectory that is fixed by this RG flow, and it's a purely saxionic trajectory. So you are moving only on the saxion. So exactly. So this provides the distance conjecture for this particular trajectory. And then the next question would be what happens if you go to different trajectories, right? So this is precisely what I wanted to say now. So, okay,
5
this is very
minutes
nice.
to 25, Irene.
How many?
5 minutes. 5 minutes to 25.
Okay, good. So I have 2 slides about what happens for other trajectories. I will go fast over them. I mean, this is older work, but since there are always questions about this, what happens with the trajectories in this type of courses, I wanted to say something. So one could think, okay, this is very nice. You get the distance conjecture for saxionic trajectories when you only move on the saxion. What happens if you consider axionic trajectories like that are turning? So the idea is that the distance conjecture is expected to apply not only to completely flat trajectories, but nearly flat trajectories like the bottom of some potential. And this can involve trajectories that are not purely saxionic, depending on what is the potential that you have. So for the distance conjecture to be true, and this is what is called also the refined distance conjecture, we need to have constraints on what effective potentials are consistent with quantum gravity, and therefore what type of trajectories are allowed. Okay, so for the distance conjecture to be true, not every potential and not every trajectory should be allowed at these asymptotic limits. So what we did also is to study what is the asymptotic form of the potential, these large field limits in Calabi-Yau compactifications. And we saw that behaves always as a homogeneous function, which means that the same amount that you are displacing in the axion, you are also displacing in the saxion when you study these gradient flow trajectories. And this implies that if you had a tower that was becoming exponentially light in the saxionic trajectory, it does the same for an axionic trajectory. And everything is just based on the fact that this one has this type of trajectory. So an open question is how general is this story, and this is something that is not settled yet. Okay, so let me just go now to the second part, the last part, which is more related to the scalar potential. So the idea is that, well, there is this conjecture that that was related to the distance conjecture in this paper, that the scalar potential always presents some runaway behavior towards infinite distance, and that can be associated to the fact that there is an infinite tower that is becoming light there. So this is what is called the de Sitter conjecture. So the derivative of the potential is bigger than the potential. And I'm putting here the word asymptotic because I'm only going to study what if this is true at these large field limits. Okay, so this is consistent with no-goes that come from classical vacua in type 2A, and we also generalize these no-goes by going beyond string weak coupling limit to compactifications of F-theory and Calabi-Yau forms. Okay, so at the moment, and all these asymptotic limits, these large field limits, there is indeed the de Sitter conjecture seems to be satisfied. But we could ask, why is this? Okay, from a more pedestrian point of view, like from a bottom-up perspective, why we should always have this runaway behavior? So let me tell you just one thing, and I will finish my talk. So there is a way to understand this runaway. If I go to a dual formulation of the scalar potential, in which, in terms of talking about fluxes, I talk about the field strength of 3 4-gauge fields. Okay, so we can dualize the scalar potential, and instead of the scalar potential, we have this term in the axion. So so now the gauge kinetic function of these 3-4 gauge fields parameterizes the potential, which means that constraints on the scalar potential can be translated to properties of membranes, of BPS membranes charged under the 3-4 gauge fields. And we can do something very similar to what we did with the string. So we can study solutions for BPS membranes, in which the tension and the charge is determined in terms of the scalars. And the no force condition that this membrane satisfies has the same form that the n=1 supergravity formula for the scalar potential. So just the last slide of the membrane. So what happens is that if we impose that the membrane saturate the weak gravity conjecture, so that the charge is proportional to the tension, one can check that indeed then the derivative of the charge is proportional to the charge itself. And since the charge is parameterizing the scalar potential, this indeed explains that the derivative of the potential is proportional to the potential, with a factor that again is related to this extremality factor. So this is a way to see that if you have a membrane that saturates the weak gravity and parameterizes your scalar potential, then you will satisfy the de Sitter conjecture. Okay, so maybe one more slide and I finished. So this is just a summary that I had from the talk. So I already gave you the ingredients, but so that it's clear in a single slide. You might wonder about these order 1 factors that we were determining through the talk. As I said, the weak gravity conjecture can just be determined in terms of the extremality. But what it's interesting is that in all these cases in which the towers of states and potential can be understood in terms of charged objects, all these factors can also be determined in terms of extremality. So the tower of the distance conjecture, when it comes from a BPS string, the factor is given by this, so gamma is the extremality factor. And these alphas are the scalar contribution to the extremality factors. So for the case of the potential, C can also be understood in the same way. And for the case, this I didn't discuss, but for n=2 in 4 dimensions, when you have BPS particles, it happens the same. So it always has the same form and can also be computed in more detail in terms of the geometric if you give some, if you use the asymptotic behavior of the Keller potential. So there is always, it's true that it seems to be that the bounds at least, in terms of the data that describes the geometric data that describes the asymptotic limits, there is some correlation between the factors that appears for the Sitter conjecture and the distance conjecture. So I think that's something to study further in the future. Okay, so this is my summary. Let me summarize. Since I think I ran out of time, maybe I can just briefly say that the Swampland conjectures get connected by the physics of the strings and membranes, and one can derive the distance conjecture and the de Sitter conjecture by using the weak gravity for these objects, and fix the order 1 factors in terms of the extremality and the geometry. So thank you very much for your attention.
Thank you very much. Let me clap virtually. There you go. Thanks a lot, Irene. Is there more questions or comments?
May I ask a question?
Oh, yes. And we have a raised hand. This is new. Sorry. Yeah. You raise the hand now. Who is asking the question? Yeah. Okay, good. Yeah, please. Very good. Very polite. Very good. Yes.
So I'm not a string theorist, but in your derivation of de Sitter conjecture from weak gravity conjecture, did you assume some information correspond to the asymptotic region, large field region?
No. So if you have that the scalar potential is completely given just in terms of these fluxes that you can dualize to the 3-4 gauge fields, and then you can understand as an extremal membrane, then you're going to satisfy the Sitter conjecture. Now, this is very constraining because here I'm saying saturating, not just satisfying. So, I mean, there is no need to saturate the weak gravity conjecture, and you could have more general situations. what happens is that you can also check, okay, when is normal, or when does it happen that you saturate the weak gravity conjecture? And that typically happens at the asymptotic regions. So you can also check in terms of the geometry that indeed at these asymptotic regions, it's easy to find well, the fluxes behave in such a way that the charge of the membranes behave as they are extremal and saturate the weak gravity. But one could go to more general situations in which they just satisfy the weak gravity and not saturate it. And then maybe one can find minima. This is something one has to study. And whether, I mean, it would be very interesting if there is some correlation between satisfying or not satisfying and de Sitter or anti-de Sitter or something like this.
You also mentioned some, I forgot the name, string, distant axion string conjecture, right? Do you have some comment on the implication of that conjecture to phenomenology or cosmology?
Not yet. So, I mean, we didn't have time to study the implications, but I think it's interesting if there is always some string, right? So at every time that you try to make some scalar field variation, somehow there is a moment in which you should be sensitive to some string, like a cosmic string. Of course, the implications will depend also on the stability of the string, right? I mean, whether it can break or not. So there are many details that one has to study and that might be model dependent. So, but yeah, I mean, it would be something.
Thank you so much.
Thank you. Any other question or comment?
So I have a short question. So do you have any comment on some local string, not and so which is charged under some U1 gauge symmetry?
So whether the string is charged under some
yeah, I mean not global string but local string, so it doesn't have any.
Well, I mean, these are charged under the two-form gauge field.
I mean, so there, so actions becomes observed. Actions are observed by some. As a Steckelberg case. I mean, so there is no like.
Okay, whether you have a BF theory, right? Like whether.
Yeah, BF theory.
Yeah, so I didn't say, but actually the story I described is valid also if you have a potential, so membranes attached to the string, and also if the string can break because you have some coupling to some gauge field, as long as the scales are below the cutoff, so the scales that are relevant for these processes. So it could be that indeed there is a BF coupling and the string can break by ending in particles that are charged, right, under the gauge field. And I mean, qualitatively everything remains the same. And I think that's the part that is more model dependent. I mean, whether you have that or not.
Okay, thank you.
Thank you. Any other question?
Could I ask one?
Okay, yes, please.
Great talk, Irene. Thanks very much for this. A question again concerning the nature of these weakly coupled strings. Can you also see that these are unique if you take a limit which does not which is not leading to decompactification? Because that would also be important, right?
Yeah, I was thinking so after the talk on Tuesday. I'm not sure if we can show that. I mean, so that enters a lot also on the. I mean, I tend to say yes, but because it depends a lot on all these constructs that we have of the different string charges, but it actually, I don't know. I mean, to be completely honest, I should think more about it, like whether we can really say for sure that there is not another string that decays at the same rate. No, that's the question, like whether it's the only one. At least for what we call elementary strings that are just like you send only one module, right? Like you go to one divisor only. I think it makes sense that it's unique, but I don't think I can prove it necessarily.
And the strings as such satisfy the weak gravity conjecture for the two-form field.
Yes.
Right. So the string excitations then would satisfy it for say other gauge fields. Yeah.
Yeah.
Is that how it's? Yeah. Okay. Thanks. Thank you.
Yes. Exactly. satisfy the weak gravity under the two formulation.
May I ask a question?
Okay, yes, come on. Yes.
A quick one. Okay,
yeah.
so thank you for the nice talk, Irene. Just one quick question. So if I understood all this correctly, there's a key point for the distant axionic string conjecture is the fact that it is a codimension 2 object, because that implies it has this strong back reaction, right? So if you try to generalize this to higher dimensions, would you expect the role of the string to be played by a string or by codimension 2 objects? And then how would you try to argue for quantizing them or towers or?
Yeah, no, that's a very good question. So indeed, everything here, what matters is the codimension. So in higher dimensions, I would expect that one has to look for codimension 2 objects as well. And then, of course, the quantization and show that there is an infinite tower of states becomes much more difficult in those cases. And even in the fact that they are BPS, I mean, it's not completely clear. So, but yeah, I think it's about the codimension, not the dimension.
Thank you.
But
Okay,
shouldn't it also always be a string? Sorry, shouldn't it always be a string? Because then you would have a theory of quantum gravity with fundamental objects not being the string.
I mean, it's not clear to me because, I mean, the thing is that the fact that there is this correspondence between the back reaction and the RG flow and moving the modular space is linked to the fact that it's a codimension 2 object. Otherwise, you lose this. So it might be that you have strings in higher dimensions, but the fact that at every infinite distance limit, you can identify some object whose back reaction, the profile that is driven by the back reaction can be understood as moving to infinite distance in this modular space. I mean, I think that has to be related to codimension 2. But it's something to study. I mean, we didn't explore higher dimensional cases yet. It could be that it's not the leading tower. I mean, I never say at any point that has to be the leading tower. And in fact, we also check that there is also some structure of how this tension behaves with respect to the leading tower. There is always some integer power. So it might not be the leading tower, but if it's always there, you can also always use it as a lower bound for the rate, for the lambda of the distance conjecture for the factor.
Okay, are the questioners satisfied?
Yes.
Let me just say one quick comment and then we change about Senyor's question. I think that one could give purely EFT argument for the breakdown or semi-classical argument for the breakdown in terms of spinning strings. I mean, you don't need to go into the full quantization of the string to argue that the EFT breaks down because the string becomes tensionless. Okay, you could talk about the spinning strings like creating a tower of states, and that's breaking down the EFT too. So we are working on that. Okay, very good.
Okay,
clap, clap.
Thank you, and thank you for all the questions.
Let's thank Irene again, and let's change track. Now we go to Korea with Pablo, who you can share a string, right or not? Can you try, Pablo?
Yes.
And,
try.
Very good.
Yeah. Is this all right?
So, yep. So our next speaker is Pablo Soler from IBS, CTPU, and he's going to tell us about Gauginos on these membranes from 10D to 4D. So please.
Thanks a lot, Fernando. Thanks everyone for joining. I'm really happy to see that my two favorite institutes get along so well. So I hope we can do this again and hopefully in person soon. As Fernando said, I'm going to be talking about Gauginos, in particular on these 7 branes and how they are described both in 10D and 4 dimensions. And this is based on some work that I've done with these great collaborators who are probably sleeping, most of them now, and along the couple last years, and something that should appear relatively soon. So, okay. So as a motivation, let me talk about the role played by Gauginos that I'm interested on, and it's the role of them as condensates, that is, as non-perturbative effects that are crucial ingredients in string phenomenology, and in particular in the stabilization of moduli and the generation of string vacua, both ADS and de Sitter. The two prototypical examples are KKLT and the large volume scenarios. My talk should apply to both scenarios. I'm going to focus nevertheless on the KKLT scenario for most of it. So one point here is that although this Gaugino condensation is crucial for string theory and string phenomenology, it's often only discussed in terms of the 4D effective theory. And this is natural since Gaugino condensation is an infrared effect that cannot be, or it's difficult to treat in the ultraviolet theory, in the 10-dimensional theory. Nevertheless, when you're trying to discuss, for example, no-go theorems or some Swampland conjectures and contrast them to string compactifications, you would want to have a ultraviolet description of these effects that are crucial for moduli stabilization and hence for the Swampland program. So the goal of my talk and of several other recent works is to understand how this effect look like from a 10-dimensional perspective. And the setup I will be working on is type 2B orientifolds with DC membranes, like the ones used for KKLT. So to go into a bit more details, even if you're not a string theorist, what you need to know about this KKLT setup is that it's at least the starting point is just a compactification of string theory that involves free-form fluxes and DC membranes that basically leads to a 4-dimensional super Yang-Mills theory, n equals 1 super Yang-Mills theory with this scalar potential and some constant superpotential that is given by the Gukov-Baffa-Witten superpotential, and below the scale of complex structure moduli stabilization is just a constant. So basically all this setup, what it tells you is that you obtain this effective 4-dimensional theory, which is just super Yang-Mills theory. You can find this Lagrangian in any textbook of supersymmetry in 4 dimensions. And what I'm focusing here is in the following terms is just the kinetic terms for the gauge field and the gaugino. The gauge kinetic coupling is given by this modulus T, Keller modulus T. And then you have a quadratic coupling for the gaugino and a quartic coupling for them. These are the two main terms that I'm going to be focusing on this talk. Now, what happens is, if the setup is appropriate, what happens is that the gauginos condense in the infrared theory due to strong dynamics. And this can be described naively, but at least it gives the right dominant terms by just giving a vacuum expectation value to gaugino bilinears that are exponentially suppressed in the gauge kinetic coupling, in the gauge coupling. So you just take this bilinear, just plug it into this Lagrangian, and you obtain a potential for the modulus T. It's a non-perturbative potential. And it takes just this simple form. And these are actually just the dominant terms of an F-term potential of an n equals 1 supersymmetric theory, where the potential is given by this standard supergravity formula. But the superpotential contains not only the constant piece, the Gukov-Baffa-Witten piece, but also a non-perturbative superpotential induced by this gaugino condensation. And this potential takes this form, and this gives rise to the famous KKLT ADS vacuum. Furthermore, if you introduce some extra ingredients, you can try to uplift to de Sitter. You can do this, but it's a very delicate process. But by adding, for example, anti-D3 branes, in order to obtain a de Sitter vacuum and not destabilize the potential, you need to be careful. And the typical scenario is to add them down a warp throat that makes this a very mild modification of the potential. If that happens, then you can see that by adding this contribution from the D3 branes, you can uplift the potential to this form and obtain a de Sitter minimum. Now, in this talk, I would analyze all these steps from 10-dimensional rather than 4-dimensional equations that I've done so far. And I will only do that assuming that KKLT assumptions are correct. whether these assumptions are valid and this uplift is actually possible is a subject that I will not discuss. Is what is being discussed very, very vividly these days within the Swampland program. And it may well turn out to be that these assumptions cannot be produced, but actually our 10D perspective, our work could help in elucidating whether this is true or not. But I will not discuss this in this talk. So this is the outline for the rest of the talk. I will start talking in order to understand how all this works in 10 dimensions. What I need to do is to understand how one can derive the 4D action from a 10-dimensional action of these 7 brains. And in particular, what is the action of Gauginos on localized brains? I will do that first on a toy model, which is a codimension one system. For example, in Horiyama-Witten theory, I will use a toy model rather. And then I will go to the full-fledged case of these 7 brains and study Gaugino interactions on these 7 brains. Once I have the proper action to study this setup, then I will try to see how Gaugino condensation occurs in this 10-dimensional perspective and how one can derive aspects of KKLT vacua from this 10D perspective, both the ADS and the de Sitter. It's the Sitter uplift. I will conclude finally. So as I said, I'm going to start just trying to define what is the action of Gauginos on a D7 brain. And as I said, I'm going to start first with a toy model, which is, again, it's crucial, the codimension of the system, codimension of the brain on the internal space. So my toy model is going to be the simplest one, is a 5D theory on just some non-compact 4-dimensional space times a circle with some localized brain on the circle. It spans the 4 dimensions and it just sits at some point y equals 0 of the internal circle. And then I'm going to add something that is analogous to the 3-form flux in these 7 setups. It's a 1-form flux, so gaugino field strength, axion field strength. We typically know, and this happens in the setup I will want to study, the action up to quadratic term, quadratic gaugino order. And this action typically takes this form, is just the gauge kinetic term for the flux, G1 squared, and then some interaction with gaugino bilinear. The gaugino is localized to the D brain, so it's localized with a delta function here. Now, this action is perfectly good, but what happens is that if I try to solve the equations of motion for the flux, I just find a flux that follows this source, this gaugino source. It's localized, and it contains a constant harmonic piece. The problem is that this localized source, if I plug it back on this on this action, because the gauge field strength is squared, the delta gets a square, and I get a divergent action on shell. This delta zero is problematic, but also notice that this divergence is at quartic ordering the gauginos, while this action was only expanded to quadratic order in the gauginos. So there's an easy resolution is to add a counter term to this action, which is quartic in the gauginos. This was worked out in these papers here for this codimension one case. And basically imposing supersymmetry, one can find a unique counter term to this action that made the action both finite and supersymmetric. And the result is very simple. It's just 2 complete squares. So here, instead of this action, we're going to have an action that is valid up to quartic order in the gauginos. And it's just the square of G of the flux minus the source. The solution is unchanged because I've only added a quartic gaugino term, nothing related to the flux. It contains this harmonic piece, and the action is now on shell finite, and it just gives you the square of the flux. This is perfectly valid solution. It's what happens in Horiyama-Witten theory. Now we're going to try to do the same for these 7 brains, which are codimension 2. We're going to see that this is much more subtle. Again, the starting point is the action valid up to quadratic order in gauginos. It contains the gauge kinetic term for the 3-form flux and this interaction between the 3-form flux and the gauginos. These interactions were derived first by Cámara, Ibáñez, and Uranga in 2004. Now we can do the same as before. We can solve for the flux, and the flux follows the source profile, so it's localized to the D7 brain. And if I plug this back into the action, I get a divergent action, which is quartic in the Gauginos. So one could try to do the same and just add a counter term, quartic in Gauginos, so that to cancel this divergence. The naive proposal would be just to complete squares here, as we did before in the Horiyama-Witten case, and to just propose this action to quartic order in Gauginos. The problem is that this doesn't solve the divergence problem. The reason is that if we try to make the source, the flux follow the source by using this proposal, localized proposal, we could see that the Bianchi identity is not satisfied. The reason is that this is a codimension 2 setup, and in the codimension 1, this was trivially satisfied. But in the codimension 2, this is no longer satisfied. So this is no longer a valid solution. This is no longer a finite action. So this is not a good proposal. We have to work a little bit farther. What we did some time ago was to propose a slight modification of this perfect square proposal. We noticed that the problem was that the source, this lambda source, localized source, was not closed. So we just said, well, why not just drop the part that is not closed? So we introduce an operator P that just projects any form into the closed, in the subspace of closed form. So that means dropping a coexact component of the source. We just propose that the action should be this one. Now G3 can follow the source. The solution is actually unmodified if you look at things properly. And this does the job. Upon integrating out the flux, you obtain a perfectly finite action, which actually can be related to the, upon compactification, to the 40 Sugra Gaugino terms in the action. It contains some flux squared, some quadratic Gaugino terms, and some quartic Gaugino terms in the action of 40, just like the standard 40 supergravity action. So this was all good. But we recently noticed a problem. This projector is a non-local operator. Basically, what we are doing when we are adding this projector, when we are going from here to here, or from the original quadratic action to here, is adding a term that scales like 1 over the transverse area of the D7 brane. So you have a D7 brane, and this area is just a transverse space in the internal space. This is problematic because when we talk about an action on a D7 brane or on any brane, we want something that is localized to the brane. These are just local excitations. So this is not what we want. Incidentally, the same type of problem afflicts another more recent proposal by Kachru et al., which was based on T-duality. And basically what happens there, I think, is that through T-duality on the branes, what they are obtaining is an action that is a smear, that has a smear branes instead of localized branes. So that's how this 1 over area arises. So what we want to do is to fix this problem and to obtain an action that is fully localized, not just some smear version of it. We've been struggling with this for a bit, but we think we have a proposal that works wonders. Basically, what I'm going to do is to look at this action in a little bit more detail. It's a bit technical, so hope I try to simplify it as much as I could, but let's see how much we can do. So what I'm going to do is to start again with the quadratic action of Cámara Ibáñez Uranga. I'm just going to include another term that I should have included before, but it plays an important role now. This is the Chern-Simons terms, which takes this form G3, which bar G3. So now we have the kinetic term and the quadratic term that couple. The kinetic term for the flux and the Gaugino quadratic term that couples to the flux, and this Chern-Simons term. I can massage this a little bit. And basically, the important part is separating the three-form flux into its imaginary self-dual part and its imaginary anti-self-dual part, G plus G minus, that satisfy this. And then I can write this same term without adding anything or subtracting anything as this. Now, this is a perfect square form, which only involves the ISD part. Then there is parts that only involve harmonic components of the flux, which are perfectly finite. And there's this delta square term here that arises because I've completed squares here. Now, the important part is that this perfect square is now perfectly finite. The reason is that G plus doesn't need to satisfy the Bianchi identity anymore. It's only the total flux that has to satisfy it. So this G plus can actually follow this source. And this is a perfectly finite term. These two are perfectly finite because they only depend on the harmonic pieces of the source. And the only divergence could arise from this term. Now we want to, oh, I should have mentioned this. What is I and J? Beside this slight generalization, I've included multiple stacks of these 7 branes and their possible, all the Gauginos living in them. This term, now I can see that it involves terms with delta I, delta J. If I is different than J, these are just terms coming from the intersections of brane stack I and brane stack J. However, if I equals J, this has a delta square, and it seems divergent. It's actually ill-defined. When I equals J, I could say, well, let me drop this term because it's problematic. But this would miss some essential ingredients in the compactification. In fact, when I equals J, this encodes information about the self-intersection of the brane stacks. So we have to be careful in treating this divergent term. In order to treat this, I'm going to manipulate this formally a little bit. And I'm going to write it as follows. I drop the Gauginos because they just come along. So I just write delta I, delta J, omega square. I change the omegas for the Keller 2 form. And then I change the scalar delta functions for scalar 2 forms that are basically 2 forms that localize an integral to the ith 4 cycle, right, wrapped by a D7 stack A. Now, if I integrate this, I get something that depends on kappa alpha beta. These kappa alpha beta are nothing but intersection numbers of the Calabi-Yau. What I've written here in this formula is I've just expanded these delta 2 forms in terms of basis of 1,1 forms. These di are just coefficients. And then I got these intersection numbers of the Calabi-Yau, which are well-known geometric ingredients in the Calabi-Yau. Now, I can see that these are interesting contributions to the action. These are finite upon integration here, but this manipulation is a bit formal. So I want to write some local action that reproduces this term, but doesn't involve these deltas squares. And we can do that. Basically, this is the result. I'm just going to show you the result. I have not changed the first 3 terms that I said were finite already, this perfect square involving the ISD flux and these other parts containing the harmonic pieces of the flux. When intersections involving these 7 branes that are different are perfectly finite, so I can keep the previous expression as well. And only when we are talking about self-intersections, I have to work a little bit further. And then I can write the 10D action in terms of some geometric quantities localized on the D7 brane. This is the first chance class of the normal bundle of the cycle wrapped by the brane. In any case, it's a perfectly local action that is actually finite, and it does all the job that we want it to do, and is furthermore local in contrast to previous proposals. Furthermore, we can do a very detailed check that upon compactification, this leads and use of some geometric properties of Calabi-Yaus, we can obtain the 4D supersymmetric supergravity action that I was mentioning in the beginning. It's quite non-trivial how this happens, but the details will appear hopefully soon. So this is the starting point of the 10D analysis that I want to do of KKLT. It took a while, but now we can start asking what happens when Gauginos condense in this action, and how do they reflect on KKLT vacua. The analysis was done in this work. This was done for our previous proposal, but it goes through the same way. As I said, Gaugino condensation is an infrared effect. So treating in the 10-dimensional theory is a little bit, sorry. Yep. Treating it in the 10D theory is a little bit tricky.
Pablo, sorry, 5 minutes to 25, since you make this break.
Perfect. Thank you.
Okay.
So, yeah, as I was saying, the idea is to try to understand gaugino condensation from this 10D perspective by simply borrowing the result from 4D theory that gaugino bilinears get an expectation value and then plugging this into the 10D action. Lambda lambda will now be proportional to e to the minus at. And we can just plug this into the 10D action and analyze where it goes. This is an approach that is hard to motivate microscopically, but it has been successful in several setups. There's many works that discuss this. A tricky point to notice is that once I plug such an exponential dependence on volumes into the 10-dimensional action, the action is no longer local. This is different from the smearing that I was talking about of branes. Even if you start with a perfectly local action, the one that I propose, once you plug in this gaugino bilinear, you get a non-local action. This is not so surprising, perhaps, because what you are doing is introducing a long-range effect, infrared effect, gaugino condensation into the 10D theory. But it's something that to bear in mind. Another caveat I should mention is that once you introduce gaugino bilinears in the 10D theory, the geometry, this induces some stress energy into the internal geometry, and the geometry should change. And it actually ceases to be Calabi-Yau or even warped Calabi-Yau, and you have to go into the realm of generalized complex geometry to properly treat the back-reacted geometry. We have not taken this into account yet, so we would like to understand the relation to generalized complex geometry better. But still, we are able to reproduce the relevant features of KKLT without taking this back reaction into account. This works as follows. Basically, the approach one follows is to consider you have a 10-dimensional supergravity action with deep 7 branes and gauginos, and you can derive the Einstein's equations in 10 dimensions, and you can trace over the internal indices. So in these ways, you can, external indices, you can trace over the 4-dimensional indices, and you can find the richest scalar of the 4-dimensional theory is proportional to this combination of stress energy tensors, involving both stress energy tensor of the external indices with internal indices. This is usually called -2 delta. Using a warped ansatz with some maximally symmetric external 4-dimensional space and some internal space, you can write this formula and integrate it to obtain that the richest scalar of the 4-dimensional metric is given by some integral of this lambda. And this is a very useful formula because you can use it by imposing positivity arguments on delta. One can obtain no-go theorems for example, de Sitter solutions with positive curvature in 4D. The starting point in our setup is a GKP flux compactification that is KKLT before taking into account gaugino condensations or anti-D3 branes. They have 0 curvature and 0 delta. So we're going to perturb this. The 10D KKLT anti-de Sitter solution with a single Keller modulus takes this formula that I just wrote and includes gaugino condensation contributions to the 4-dimensional curvature. This can be read off. This contribution of lambda is just a stress energy tensor, which can be computed from the 10D Lagrangian that I presented in the first part of the talk. What we do is just plug this gaugino condensate into that 10-dimensional action and derive a formula for the 4-dimensional curvature. And we can see that it matches the leading terms in the KKLT potential. And actually it leads to a ADS curvature. This is the same as KKLT ADS result on shell up to small corrections. Similarly, we can add anti-D3 branes, so we no longer have only contributions from gaugino bilinear condensation, but also for anti-D3 branes. And assuming they are warped down, basically you can neglect this because there is a very, very high warp factor in front of them. even if they are negligible, one can show that there is uplift to de Sitter because the same formula for the gaugino contribution to the scalar curvature now gets modified on shell because the value of the Keller modulus on shell is slightly shifted by the presence of this anti-D3 brane component. So one can also show that in this case, the 4D curvature obtained in this 10-dimensional approach also matches the result by KKLT. So we have a full agreement of KKLT, at least to the leading orders of KKLT. So with this, I just wanted to conclude. I just summarized by insisting that the 10D perspective is crucial in understanding string theory constraints on compactification, and in particular, testing Swampland conjectures about ADS or de Sitter or any other conjecture for that matter. In order to test the KKLT proposal, we had to study what are the actions of gauginos on these 7 branes, and we proposed local finite action for quartic terms, in quartic gaugino terms on the D7 branes, and this avoid previous problems of and reproduce the expected 4-dimensional supergravity results. We have also checked that the 10-dimensional and 4-dimensional approach to KKLT are compatible. And as I said, this is nice and this can serve to further analysis, but we have not analyzed yet whether KKLT itself, the underlying assumptions, are correct. And this is the subject of very, very intense studies elsewhere. And hopefully we can come back using our proposals. Thank you very much.
Thank you very much, Pablo. Let me also virtually clap again. Thank you. Clap. Are there any questions? Comments? Yep.
So if you can go to this point where you said like, okay, we have this non-local action, let's make it local.
Mm-hmm.
It was the first time I see how you're doing this thing. I just wanted to understand the details.
So this is the non-local proposals?
Yeah, okay. I think it was the next slide. Yeah, this one.
Yeah.
So what you're doing is you're adding and subtracting this, well, super localized term. Is that right?
So here we isolate the divergence, basically. Yes, so we complete squares. We combine this gauge kinetic term with this interaction into a perfect square here.
Yeah.
Upon solving for this ISD flux, this is finite, but then you're remaining with this term that was left because I completed squares. And this is the ill-defined one, the problematic, possibly divergent one.
And then you were saying that this guy that has these 2 Dirac deltas is related to the, well, what was it, Asymptotic class, or what was it?
Yes, so this involves, like, if I is different than J, so that is 2 different stacks that are intersecting, this clearly localizes to the intersection. But this is a finite object.
Yeah.
What is more subtle is that when I equals J, this object, and this can be obtained by this manipulation. If I is different than J, this is perfectly valid. And this just tells you about intersection of different branes. When I equals J, I can formally do the same manipulation, and this can lead to K alpha. So the self-intersection of Calabi-Yau, which of 4 cycles, which can be non-zero as well. So what I need to do is to find or what we did at least, is to find a local 10D expression that reproduces this self-intersection property, and this is this term here. If you want this first-gen class of the normal bundle, it tells you how to deform a 4 cycle, and that helps you in understanding if that 4 cycle has a 0 section. It tells you about the self-intersections of that 4 cycle.
I see. Okay, well, thank you.
So we have another question from Thomas. Please, Thomas, go ahead.
Thank you very much, Pablo. I think it was a really clear talk. I still have a general question, which is something that keeps on confusing me. So you achieved, if I understand correctly, by So the new ingredient is really looking at these self-intersections, and they really give you a local action in 10 dimensions, okay? If I understood it correctly. But
yeah,
then,
so yeah, they might be absent.
Right, but then you admit that you kind of give up locality the moment you want to discuss the effect in the Einstein equations, okay?
Right.
So I'm a bit confused by that. So why are we okay? Why is it so important to have a local action at some point, but then we give it up? And then a related question, and I think it's only one question. How sensible is it to think about a local gaugino action given the fact that gaugino condensation happens on a scale far below the Kaluza-Klein scale? And relatedly, yeah, you said we can discuss like the back reaction potentially on a Calabi-Yau, but is that meaningful given that the fluctuations of gaugino condensation is so much larger than the full Calabi-Yau itself?
So let me answer the first question first. There's two types of no localities that I've discussed this. The first one is the one that I've talked about here, this type of smearing of a brane. So if I look at a 10-dimensional theory with these 7 branes, so far in this part of the talk, I've only talked about gaugino interactions, not about their condensations. I didn't need to assume that they condense or anything. Gauginos are open strings attached to the D7 branes. They should live in a theory that live on the brane alone. They shouldn't be, there should be no dependence on the transverse volume. This does not rely on any IR effect like gaugino condensation. There is not such a thing. It can be perfectly well described in a UV theory, in a 10-dimensional theory. I should not expect any. It says my internet connection is unstable. I hope you can listen. In any case,
it's fine.
Okay, the gaugino interactions should be a local on the D7 brane. There's nothing weird about them. I don't see any reason to expect any non-locality on the theory on a D7 brane. What you are doing next is to go and try to study gaugino condensation, and that then, as you are saying, it's a deep IR effect. It happens below the KK scale. So there's no good reason why I should be able to discuss it in the 10D theory. So now we are talking about something different. We are trying to put back something that is on a large IR scale and plug it back in a UV theory. And the price to pay is that this long distance effect, when plugged into a 10D theory, it induces this non-locality. Now, as I said, it's difficult to motivate by first principles why this approach of giving a gaugino condensate ABF in 10D works. But if it works, it seems to be this way. I don't have a microscopic understanding of why it is, but I'm not too surprised that it leads to a non-local action. I don't see an incompatibility here. We are talking about two very different types of non-locality. I am certain that the first type of non-locality should not be there. A D7 brane action should be localized to a D7 brane. Once I include gaugino condensation, things can become more complicated. The second question was related to this. And yeah, I don't know, as I said, it was just whether this approach makes sense or not. And it seems to give reasonable results. There are arguments using anisotropic Calabi-Yaus and different type of compactifications that this could work, but all that I can say is that it has worked successfully in other setups. Maybe other people have a better motivation for this. I'm not sure if I'm leaving something out.
No, we can sure discuss more, but maybe offline. Yeah. Thank you.
Okay. Anyone else? Well, I have a quick question. So this expression with the 7-brane intersection, have you tried to dualize to heterotic to see what it means and see if it matches the expressions that we have there?
Not really. But so, for example, no, we haven't had time to do basically anything more than deriving the 4D action. So these are interesting questions. But using T-duality is tricky because precisely this is how this other proposal arose. These people try to obtain a quartic action for Gauginos on these 7 branes using T-duality. And the problem was by T-duality, one was smearing the branes. So something that was local became non-local in the dual theory. So maybe we have
that I understand, but since you are expressing things in terms of topological invariance, these things have a nice, I mean, you can do an educated guess, know what these things mean if you have a iterative with bundles and maybe try to see if it matches morally if you want before doing it, without doing this. And another question, so this expression is without word volume fluxes or they don't matter?
We haven't, I'm not sure if it matters, but we haven't introduced it yet.
Okay, thank you. So anyone else? No, well then let's thank Pablo again, like this, virtually. Thank you very much, Pablo. And let's change tier, let's change continent again. Now we are going back to Europe. And we have Alessandro Menino. Oh, he's already here, very good. With from IFT, who is going to tell us about this very long title that says discrete symmetries with coupling, conjecture, and scale separation in ABS vacuum. So please, Alessandro, proceed.
Oh, hello, good morning, everyone. Well, depends. Hello, everyone. So thank you, the organizer, for letting me present the work that I've done with my supervisor, Angel Uranga, and my colleagues, Ginevra and Jose. I know that maybe someone has already listened to me presenting this paper, also Angel in the past. I hope that they can still enjoy the presentation. And I would like to give you like some new perspective, some new idea, also for the people that never heard about this. So in fact, what I am going to speak about is the role of discrete symmetries in the Swampland program. We indeed think that they play an important role. And in fact, this important role for us has been realized in the proposals of a new conjecture, which is the weak coupling conjecture. And also we say we have a refinement on the distance conjecture, Untitled de Sitter distance conjecture, because we think that also we have seen that the presence of a discrete symmetry can explain the scale separation that have been observed in some example of type 2A compacification with flux vacua. So let me say again, of course, there are a lot of Swampland conjectures that have been already discussed in the previous talks and also on Tuesday and today by Irene. And the hope, the aim of the Swampland program is, of course, to find some constraint of the effective field theories that are compatible with quantum gravity. However, most of them, they focus on continuous gauge symmetries, and only a few of them, and very recently, there has been talk about constraints coming from gauge discrete symmetries. So our intention, in fact, is to focus on this particular case and see what can we say about the discrete symmetries in the Swampland program. So I'm going to give you some introduction, and also I will state the conjectures at the beginning. And of course, when I speak about discrete symmetries, not everyone may know about them, how they work. So I will give you also a review of how can you realize that a discrete symmetry is present, how they present in Lagrangian, and I will focus on abelian discrete symmetries. Then I will come to the main part of the talk, which is the presentation of the two ZK conjectures that we are proposing, and I will present them by examples, selected examples that they are present in the paper, and they can be also useful to understand the motivation why we think that these conjectures are correct and important. So let me go on the introduction. You can interrupt me anytime if you have a question. This slide will be repeated at the end of each section. So if you want to stop me there, you can ask me about what I have already said. So the idea is that, as I said, to see if there is a quantitative link between discrete gauge symmetries and continuous gauge symmetries. And in fact, see what is the nature of the nature discrete symmetry in theory of quantum gravity. The weak coupling conjecture that we propose have been tested in many concrete string theory example, in holographic example, for instance, that they are the one that I will present today. And also we think that the discrete symmetries coming from three forms play an important role in the problem of scale separation. And for these reasons, we have proposed a refined strong anti-de Sitter distance conjecture that we have tested in a type 2A ADS vacua obtained by Calabiao orientifold compactification with fluxes. So let me first state the conjectures so that all of you have in mind what we are going to test. And the weak coupling conjecture say that if in a theory of quantum gravity there is a continuous U1 with coupling G and also a discrete ZK gauge symmetry with K is the order, then the gauge coupling has a scaling with the order of the discrete symmetry with K to the minus alpha, where alpha is a positive order 1 coefficient. At the same time, we have proposed this refinement of the strong anti-de Sitter distance conjecture that say that in a theory of quantum gravity on an IDS vacuum, if there are ZK discrete symmetry for domain walls and with K large, then in the flat space limit, there is an infinite tower of states which comes cutoff M, and the cosmological constant scale with M square over K. So let me move on to the description of these discrete symmetries. And the prototypical example of a discrete symmetry can be the X model, or in particular when you have a continuous U1, which is broken by some scalar web with expressed like here, like this. And then we will focus on the phase of this scalar field, because after that you have integrated the massive, integrated out the massive mode, then you will have that the phase have this action in this form, and there is still a residual gauge invariance, and you can shift the gauge potential by a factor the mu lambda, and then also the phase is shifted by lambda times k, where k is this integer factor of the ZK discrete symmetry. However, this is not the only way in which you can find that you can identify the discrete symmetry, because you can go to the dual description with the usual BF coupling. And this is very common in the string theory compactification, and they are usually a way to tell that there is a discrete symmetry. In fact, defining the dual field coming like a dB2, and then using the strength, the field strength F2, you will have an action of this form with this B2 wedge F2 coupling. And to see better the discrete symmetry, so in particular to write it in a similar way to the previous example, you can use the dual magnetic photon of the F2, and you will see now that if you shift B2 by a D lambda 1, then also the A1 tilde is shifted by a factor K. So there is a very similar gauge invariance. It's only one form higher. So, but what are the objects charged under this discrete symmetry? Then, of course, the first example was talking about ZK charged particle. but also in the dual description, they are ZK charge strings. And in particular, the gauge invariance means that the K particle can annihilate into an instanton, and K strings can annihilate in a monopole line. So there are many pictures of this, can be drawn. However, these are not detectable by long-range fields, but well, there are no long-range fields, but they are still detectable, because when a particle, for instance, move around charge strings, both of them charged under this discrete symmetry, then it will pick up a phase, an Arabon-Bomb phase. So they can be probed anyway, the presence of this ZK experimentally. However, the problem is usually it's not easy to identify the underlying U1 from which the ZK symmetry derive. And I will do some example later on in the case of the weak coupling conjecture, in which not always the U1 can be explicit, and we will look at that better. However, you can also generalize, as I was saying also in the dual description, you can generalize this story of the discrete symmetry also to higher P forms in any dimension. And then you can have P+1 form eating up a P form, and all the dual description that I've said before with the BF couplings. One in particular that we will use in the second part of the talk is the one that is called Calober-Sorbo coupling, which is corresponding to a -1 form. And when you have an action of this kind here, when there is a coupling Phi5F4K with a factor K, then to identify the dual symmetry is sufficient to go to the dual action to see better the discrete symmetry. And as you can see, it's very similar to the case that we have seen before with the BF coupling. But in this case, the gauge invariance is given by a shift of the 3 form, and then which is also related to a shift of the B2. In this case, the charged objects are K domain walls that annihilate into a string. The domain walls will play a role in the second part of the talk. And just to mention, I won't talk about that, but this is more or less similar to the axion monodromy setup, in which introduced by Silverstein-Westphal some years ago. And where there is a scalar which has a fixed period which is scaling this way. So now we have all the instrument to go to this talk about the ZK with coupling conjectures. And the ZK with coupling conjecture, as I was saying before, is this. Now you can see that very big on the screen, and you can remember it better. And then you have this gauge coupling. We need to identify this gauge coupling of the continuous U1 and see how it scales with the discrete symmetry ZK alpha by a factor alpha, which is a positive. Let's move immediately to the example. So the first, also easier example that you can look at is the classical type 2B string theory on a DS5 S5 mod ZK with n units of 5-form flux. These are Quivers theories and very n equal 1 or n equal 2 gauge theories in 4 dimension. And then in here, I'm talking about S5 just because it's easier. But it can be generalized to any toric Sasaki-Einstein manifold, but also non-toric, any Sasaki-Einstein manifold. In particular, here there are continuous U1s that are coming from the isometry of the internal space, and we will call them mesonic. And there is, of course, the R symmetry, which is the most important. And in the example, I will focus on that. But whatever I am saying, if you choose the other U1s, then the weak coupling conjecture will be true anyway. What are the discrete symmetries? Well, the discrete symmetry is not only the ZK as we can imagine, but there is a bigger group, which is the Heisenberg group. This Heisenberg group, it's easier to see at the level of the quiver because, for instance, when you have a more gauge group, all of them with the same rank, then you can shift or redefine the gauge group like a rotational symmetry, and this is a ZK symmetry by that. And however, there are other operators and they don't commute, A and B, this operator don't commute, and the relation is contemplating also a central element C, and so they satisfy AB equals to CBA. And just to mention, we did a work with Angel and Eduardo 2 years ago now, well, last year, about the identification of these discrete symmetries at the level of the field theory for any toric Sasaki-Einstein manifold. However, the particles that we are interested in now in the gravity perspective are this D3 brane wrapped on torsion 3 cycles. And in particular, we want to look at the one with minimal charge, which is the one that is wrapping the S3 at the equator. And they are usually called D baryons or giant gravitons in the IDS. So what we do is to take the usual definition of radius and Planck mass in ADS 5 across S5, and then we can rewrite them using expressing all the quantities in terms of the factor k's which appear of the orbifold. And also the mass of the D3 brane can be found by usual relation where the R3 is coming because it's wrapping this S3. And then you can use also KK reduction from 10D to 5D to identify the gauge coupling constant of the U1 that we are looking at. And as you can see, there is an actual dependence of G by K, and this factor 1/3 is exactly the alpha that we were looking at. And just to be sure that we are consistent and everything is working fine, you can obtain the same relation if you impose that, well, if you use the BPS bound coming from the weak gravity conjecture, since these D3 branes particles are BPS. If you use the BPS, the weak gravity conjecture, you will recollect the same factor K. So we are okay. Now I can go to a different example in type 2A, and I'm talking about the famous ABJM model that has to the interpretation in terms of M theory on IDS4 times S7 mod ZK with n units of S7 for flux, or in the type 2A perspective, which is IDS4 times CP3 with n units of 6 form flux and k units of 2 form flux. I will focus on the type 2A perspective. Again, here there are continuous symmetry coming from the isometries and also from the R symmetry. That is the one that we are interested in, but well, not in particular in this case. Anyway, it's more complicated. It's not easy here not so immediate to identify the U1 that we are looking at. For instance, because the discrete symmetry, as I was saying, is hidden. It can be found when you compactify the Chern-Simons term in 10 dimensions, and you will end up with the sum of 2 BF coupling. As I was saying in the abelian discrete symmetry case, they are a symptom of discrete symmetry. This is come from the integration over a CP3 of the F6, and this is coming from the integration of over a CP1 of the F2, and then also a CP2 for the S6. And then I can identify 2 combinations of U1s. One is the one that is broken by this BF2, which is a Q, and the other one is the massless U1 that we are looking at. And the charges Q and Q are related to the object that are charged under this F2 and F2 prime symmetry, which is the D0 and the D4 branes. How is the discrete symmetry? Well, the discrete symmetry is of order n square plus k square, which is the violation of the Q the broken charge. And the meaning is that if you have n D0 brane with charge n, and also k D4 branes with charge k, they annihilate to the vacuum. And so this is why the order of the symmetry. And you will find details also in the paper. And if I redo the story again, I can rephrase everything in terms of the mass of the D0 and the D4 brains. I will have some scaling with Ks. And also I can look at the Chern-Simons terms of the brain and the charge normalization to determine the gauge coupling constant of the D0 and the D4, under which the symmetry are coming. And as you can see, you can define the effective coupling constant of the massless U1, and you will have a scaling by a factor of 1/4. So it's satisfying the weak coupling conjecture. This same story can be done also looking at the weak gravity bound of the BPS particles, and everything is consistent. And one remark that I would like to do, because this example will come back again later, is that in the ABJM, you have two different states that are BPS, which are the D0 and the D4. Then you have identified a charge under this U1, which is left unbroken by the BF couplings, and they have charge K and charge N. And under this J, so the D0 has charge K and the D4 has charge N. And they are consistent also with the gravity bound because they are BPS objects. So using just the information of the symmetries, in this case also the fact that the particles are BPS, you can find a relation between the two gauge couplings, the D4 and the D0, they need to scale in this way. It's easier to see also if you look at the definition of the effective coupling constant, since we have an effective coupling constant that is scaling like this, and then you see that the D0 and the D4 needs to scale in particular way. So the ratio follows just from the symmetry and the BPS condition without knowing anything about the details of the compactification. This is just a remark. It is not useful maybe with the coupling conjecture now, but it will be later on useful now that I am going to speak about the refined strong and the de Sitter distance conjecture.
Alessandro, 5 minutes to 25.
Perfect, in time. So let me review the first what is the problem of the scale separation. Everyone's know now what is the distance conjecture. I think that have been already said at least twice, and what is it? And so in general, there is when you have a quantum gravity theory and with some cosmological constant lambda in an ADS space, then there is this tower of states that behaves with a cosmological constant like lambda to some alpha, with alpha as positive number. The problem, there is also a refinement of this de Sitter distance conjecture, which is the strong one. We say that in the SUSY theories, this alpha needs to be equal to 1 alpha. And there are many examples that satisfy that. All the holographic cases that I have seen before, that I have described before, they satisfy. However, there are examples in type 2A flux vacua in which the strong anti-de Sitter distance conjecture seem to be violated. And these are DGKT vacua, all the kind of DGKT coming from this example by the Wolf and collaborator, in which they have this ADS vacuum in which the cosmological constant and the mass doesn't violate the mass of the KK violates the strong anti-de Sitter. What we want to show is to prove is that actually this DGKT vacua can be a reason why the strong anti-de Sitter distance conjecture should be refined by a ZK discrete symmetry, considering using the discrete symmetries. So let me first review a little bit the DGKT vacua. They are compactification in type 2A. In particular, the one that we are looking at is the vanilla one, the DGKT true. So in T6 over Z3 orientifold with 6 planes, and then you will have Roman mass and NSNS 3-4 flux, which contribute to the tadpole, and they are bounded and order 1. So because of the tadpole condition. And there is also the F4 flux, which is instead left unbounded. There is no condition on that. And they used this unboundedness to study the solution when you go to large flux, K, F4 flux. So they define this factor K, and then from your theory, you can define all the scaling of the moduli and the parameters by this factor K. And you will find then that the vacuum energy is scaling with K to the minus 9 alpha, and also the KK modes are scaling with minus 7/4. And you will find that the strong anti-de Sitter distance conjecture is violated, because now M square KK is scaling differently by 1/2, is 7/18. But what are the roles of discrete symmetries in these examples? How to use them? So first, let's rewrite that in the relation of before in this way. It's very close to the refinement that we have done with the distance conjecture, if you remember the conjecture at the beginning. And now we just look at as I was saying in ABJM, just look at what you have in your theory. You have a Chern-Simons term in 10D, and then you compactify them, knowing that there are F4 flux, the same fluxes of DGKT, but you just compactify your theory. You obtain this Calover-Sorbo term when you compactify this Chern-Simons term, but there are also other Chern-Simons in 10D. For instance, this one is with a Roman mass B2 at F8. Then you compactify in 4D and you find another Calover-Sorbo term. And choosing a particular combination of charges coming from this combination of this number E bar, you find two Calover-Sorbo terms, very close to the ABJM, right? It is not a BF coupling, it's a Calover-Sorbo. So there is a discrete symmetry, no? And in particular, there is a massless three-form symmetry which is left unbroken, so by these terms, and there is also an approximate ZK symmetry, since we know that the M is small, is order 1, K can be whatever, no? So we are going very large, so it's approximate ZK. And now we can just look at the object charged under these symmetries here, the U1 under this U1 left unbroken, and they are D2 branes, domain wall, and D6 wrapped on 4 cycles domain wall. We compute the gauge coupling, and it's very close, no, to the one in ABJM. So we are just using a symmetries condition. We are not looking a specific example, right? And then if you compute the gauge coupling of the domain wall from general toroidal compactification, no, the general, you can find a relation between this gauge coupling with the parameter inside the with the moduli of the compactification. And then, since as I said before, no, there is a way to know what is the scaling of the gauge coupling between themselves using this relation here of the symmetry. And so you can find how the moduli should scale with K. And also the presence of flux gives you this flux monodromy and potential, no? And this is a generalization of the DGKT case, because this is not just a torus, so there is a triple intersection number generically. And then using the monodromies that you can generate just for all the moduli, then you can understand the scaling of these NSNS moduli phi, which before was B, and then also of the three-form axions and the dilaton that must scale like that. And then with just this for information, you can compute the KK modes, the KK mode mass. Finally, you can play still the game of this, the plane of just knowing the symmetry, and then you compute the tension of domain walls. And in using the tension of the domain walls and also the gauge coupling coming from generic compactification, you can use, for instance, junction condition, junction formulas by Randall Sondrum, very famous, to know what is the vacuum energy. And so from the tension, you just, since the tension of the D4 brane domain walls is the one that is changing the value of K, you just variate K and you know what is the value of the scalar potential, and then you can derive lambda. And so we have recovered the same scale separation of DGKT without explicitly looking at the DGKT example. And let me just conclude here, because I think that I am of time, stating the conjecture, because as I said, the fact that we have used just discrete symmetry information to find this scale separation, let us make a refinement of the strong anti-de Sitter distance conjecture, saying that if there is a discrete symmetry, then in the flat space limit, the cosmological constant should scale like this with the cutoff of the infinite tower of states that with form. So I will leave you with the slide with both the conjectures, because they are the one that you can ask if you like ask question. But first, let me thank you everyone for the attention.
Okay, thank you very much, Alessandro. Let me also clap. Very good. Thanks a lot for the nice talk. Are there any questions? Thomas, you're raising your hand, or is it the previous one?
Yeah, that's correct.
That's correct. Then please go ahead.
Yeah, I can start with one question. There are also type 2A solutions without Romans mass, which feature or claim to feature scale separation. But from your explanation, I would say I would lack the correct Chern-Simons terms to make your procedure work.
So you say that there is no this term here, right?
Yes.
Yeah, but since, well, we are, this is the term which is scaling with K. So the other term is because it's present also in our theory, and then you can generate two Calober-Sorbo term. But if you don't have this, you still have a pure ZK symmetry, I think. So okay. In this case, it's approximate because there is M, and then we say, okay, M is order 1, then you look at the large K limit, then you can forget about this. But if you from the beginning don't have it, I think that is also a better situation.
Okay, thanks. And if there's no other question, maybe I can ask another very quick one because it's very simple.
Go ahead, have a blast.
Yeah.
Yes.
You were explaining how the gauge coupling for U1 would scale with the discrete symmetry parameter, and you were giving various examples, and one of them was ADS5 crosses 5 over ZK.
Yes.
But I'm slightly confused now. So would you also have for ADS5 crosses 5 over ZK that lambda goes like M squared KK over K? Because I thought that solution was not scale separated.
No. In fact, in all the ADS example that we have tested, when you compute the scale to compute the quantities to check if there is a scale separation, you actually find that the cosmological constant and the radius are scaling the same. Well, they're scaling like the conjecture is, so lambda is going with R to the minus 2. Despite the presence of the discrete symmetry, well, the fact is that the problem with the scale separation in the type 2A flux is that the lambda is scaling with K with some power, and R or the KK modes are scaling with a different power. In the old holographic example, they scale the same by a factor 1/2. So there is no scale separation there.
Okay, thank you.
If I may add a comment.
Yes, Angel, please.
A difference between the two cases is that in the ADS5 example, the discrete symmetry is for charged particles, whereas in the ADS, for example, the discrete symmetry is for domain walls. So there is a difference of the discrete symmetries in both cases, and that would it's tantalizing to think that this explains the difference, that there is no scale separation in one example and there is in another.
Okay, that helps. Thank you.
Yeah, I'm sorry. Yes, I also forgot to say that. Yes, the refinement is about discrete symmetry for domain walls.
Very good. Is there any other question or comment?
May I ask a very basic
question?
So in the first conjecture, are you thinking of an ADS vacuum or whatever vacuum? Is it supposed to work for any vacuum?
For any quantum gravity theory, yes. The example that I have done, they are in non-holographic example because they are like more concrete, at least from all the quantities that they are, but there is also a black hole argument that we have given, which is heuristically should be valid for any, in general. So also for any kind of quantum gravity theory, yes. They are just a selected example in which I use the holographic dualities to test it.
But this is supposed to work for only a large K? Or when you say for large K?
For large K, yes, well, we haven't found a bound on K, but for large K, you can easily identify the scaling, of course, because we are looking at the behavior of the quantities, how they scale with K. So large K is easier to avoid like cancellation, accidental cancellation. So this is just a large K to be able to identify the correct scaling of the quantities. In the holographic example, it's quite easy because all quantities can be defined exactly, so you can actually identify immediately what are the scaling with K. So I would say that in the holographic perspective, it can be true for any K. Of course, I have a look at the type 2A version of ABJM, and then there are conditions under which this version is valid. But anyway, yes, in those cases it's always true. Of course, we are always talking about supersymmetric cases, so we don't know in the case of non-supersymmetric.
Okay, thank you.
Okay, is there any other question or comment? But if not, let me just make a final one, well, directed to Alessandro or anyone in the audience. So there is lately this trend of connecting all the different conjectures that are on the table, all the Swampland conjectures, and the distance conjecture is not that isolated case. So people have tried to connect to the other conjectures as well. So it seems that if you refine one of these conjectures, which is one of our favorite words in this business, you should look at through these connections to how you would refine the other. So can you think of other connections that you have to refine if you refine this one, or not really?
Well, there has been work on refinement on with gravity conjecture related to the discrete gauge symmetry. So, and I think that when you talk about discrete gauge symmetry, you should well, we should be able to refine all of them considering the discrete. I would say that the first one that maybe we can try to connect with the one that we are proposing is the with gravity conjecture now, but I don't know in particular how to refine it differently on how they have already proposed in the Garcia and collaborator paper, I would say. Yeah, I need to think about the other.
Okay. Good. So thanks a lot. Let's thank Alessandro again for nice talk. Yeah. So, and then, well, I think we are led to the discussion. I'm sorry we are a little bit late, but I think we should do this 10 minutes so that people can at least go to the toilet. So, so we meet back in 11:45. Is that okay? It's 10 minutes, right? Yeah. 11:45. Senor, are you okay with that? Next chairman, please.
Yes, it's 6:45 here. Yeah.
Oh, I'm sorry. I'm so sorry. Yeah, 10 minutes.
Yep.
Okay. See you guys.
Okay, I guess it's about time. If you're ready, Pierre.
Yes.
Okay. So welcome back, everyone. This is going to be the last session for the stringy part of this workshop. This is going to be relatively more formal than the others, but still fun. So so we are pleased to have Pierre Corbillane from IFT. He will tell us about 6D n equals 1,0 anomalies on S1 and F3 implications. Please.
Yes. So first of all, let me thank the organizer for giving me the opportunity to speak here and present my work, which appeared earlier this year. And indeed, it's going to be a bit more formal, so about anomalies and F-theory implications. So it's not directly related to the Swampland program, which is the focus of this set, but it's still connected. So, I mean, we've already seen this picture 2 days ago and this morning as well. So the Swampland program, which aims at differentiating between those low energy EFTs that cannot be embedded in quantum gravity or string theory, while as opposed to the Swampland, the landscape, which can, those that are in the landscape. So to understand the boundary between the landscape and the Swampland is the aim of Swampland program. But it's already assumed that those in the Swampland are anomaly free. So the bigger picture is that you have the set of all EFTs you could write down at low energies. Some of them are suffer from anomaly, which you can already see without going to quantum gravity arguments. And well, the Swampland only refers to those which are already anomaly free. But so it's also important to understand better the anomaly, the boundary between the anomaly free and the anomalous theory, which is, there are still things to discover here. So this will be the subject of my talk. And also because we're interested eventually in string theory, which can admit different dimensionality for its effective action, we will be interested in to understand how anomalies translate from one dimension to the other. So in the simplest case, on a circular reduction. So we will be speaking about 6D anomalies. So let me start with the simplest case, where we have a chiral fermion in 6D, which I denote psi, which has an charge Q under this an abelian gauge field for simplicity, which I denote A. I put a hat to say that it's 6D because later on we will be interested in compactifying this on a circle, and the quantities without hat will be 5-dimensional. So this theory has a well-known anomaly, which is proportional to the F to the 3 and the force power of the charge, which can be seen most easily from the box diagram, which is the equivalent in 6D from the usual triangle diagram in 4D. So this comes from the anomaly polynomial, which is the force power of the gauge field, or of the field strength. And if one generalizes this setup to several fermions, which I put an index F, and several gauge field, where I put an index I, then the anomaly takes the following form. So now we are interested in looking at this theory not on any 6-dimensional manifold, but one which has a circle. And then look at the effective theory on the 5-dimensional manifold when we look at energy much below the inverse radius. So in 5D, there is no chirality. So it seems there would be no anomaly. But so it would naively seem that imagine we start from a theory which has an anomaly in 6D. Then in 5D, we don't see the anomaly. So it seems that we go from a theory which is inconsistent to one which is consistent. Well, this cannot be. We know that, so from physical principle, evil should be concept, which I denote by this equation. So this, somehow we should be able to see the inconsistency in 5D. And this we already studied in this in a paper 2 years ago with Thomas Grimm and Diego Regalado, where we looked at this question in the 4D setup. So we started from a 4D theory which was anomalous and going to 3D. And we saw that the theory seemed to be consistent, or at least gauge invariant, in 3D if one uses the zeta function regularization. So this is not consistent with this, what I mentioned earlier. But on the other hand, if one uses the regularization which preserved UV symmetry, and I will explain later on in what precise sense, the 3D theory was non-gauge invariant and actually varied as it should. So we're going to do the same thing, but for the 6D case. But in that paper, we also saw that if one starts from this 4D anomalous theory, then, as I said, the 3D regularization matters. While if one starts from an anomaly-free theory, so you can add several fermions, such that the sum of the cube of the charge vanishes, then the theory has no anomaly in 4D, then the regularization you use in 3D does not matter. So you could say, well, I don't care about anomalous theory, I only care about anomaly-free theory. So why would I care about the regularization? Well, the point is that in 6D, you cannot add fermions with such charge so that the anomaly cancels, because you can never cancel the force power of the sum of the charge. So you are forced to use the Green-Schwarz mechanism to cancel the anomaly, which adds to the action the following terms. So schematically, so you have the two form B, which with two Fs, so this topological term. And then, so this two form B is naturally present in 6D. And if you ask that it varies in such a way, then this term is classically non-invariant, and it can cancel the one loop variation if you require that the following condition is satisfied. So diagrammatically, the box diagram we had earlier is cancelled by this three-level diagram. And because these two pieces which cancel are very different on nature, one is the one loop variation in 6D, and the other one is the classical non-invariant, we expect that the 5D regularization always matters. It's like, in essence, it's like if the theory was anomalous at one loop, it's cancelled by the classical piece. And we will see that this will have various implications for F theory on Calabi-Yau threefolds. So from now on, I will focus on supersymmetric theories. So theories with 1,0 theory, the minimal amount in 6D. So such a theory has several multiplets. So there is the gravity multiplet, there are also tensor multiplets, vector multiplets, and hyper multiplets. And I will take the gauge field are in the vector multiplet, and I will take them to be all abelian for simplicity, denoting them again by this index I. And then only all the chiral fermion charge under this gauge field lie in the hypermultiplets, and only a subset of them needs to be charged. And here I denote their charge by QIF for each fermion F. Then the anomaly is proportional to this for quartic term, as we saw before. And then the two forms that are needed for the Green-Schwarz mechanism, they lie in the tensor multiplet and in the gravity multiplet. And the Green-Schwarz terms takes the following form, so as the B that we saw earlier. And then this dot means construction with the SO 1,NT metric. Okay, and then as we saw, the anomaly cancellation condition generalizes. Well, we don't see it yet, but tell you, it generalizes to this form. So here, this 4 index guy is just the symmetric product of these Green-Schwarz coefficients. So the theory will be anomaly-free if this condition is satisfied. Well, that is just for the pure gauge anomaly. Then there are also other anomalies. There is the mixed gravitational gauge anomaly and the pure gravitational anomalies, which here are the conditions. So this, in order to cancel them, you need to add another Green-Schwarz term with this coefficient A, and then all the anomalies are cancelled if these 4 equations are satisfied. Then if this is the case, you can write an action for this theory, which is gauge invariant. So here you have all the kinetic terms and the Green-Schwarz terms. And now our goal is to reduce this theory on a circle and see what happens to the anomalies and the fact that it's cancelled via this Green-Schwarz mechanism. So here are our reduction ansatz. So the 4D gauge field give rise to the 6D gauge field gives rise to 5D gauge field and some scalar, which I denote zeta, which are also the Wilson lines. Here the A0 is the graviphoton. And similarly, the 6D two forms give rise to two forms in 5Ds and vectors in 5D. But in 5D, you can dualize the two forms into the vectors, into a vector. So you can go to a framework and there is only vectors. So this we will do. And we will look only at the Chern-Simons terms because we're interested in anomalies. So it's enough to focus on the Chern-Simons terms, which are these A wedge F terms. So here are the terms you get by performing the circle reduction classically. So there is the first line, which is gauge invariant. And there is the second line, which you see depends on this scalar zeta. So it's not gauge invariant in 5D. And this was to be expected because we started from this 6D action, which has these Green-Schwarz terms, which are not gauge invariant at classical level. And you see this Chern-Simons terms indeed depends on this coefficient B, which is related to the Green-Schwarz mechanism. So all these terms come from the Green-Schwarz terms. And so we expect those terms to vanish once we include the one loop corrections. And this is what we will do in a moment. But first, let me mention that this theory still has a supercharge, so n equal 1 in 5D. And the canonical form of such of the vector part of this action can be written in this form, and where everything is given in terms of one function, the pre-potential, which is cubic in the coordinates, and has this k, I, j, k coefficients are the Chern-Simons coefficients. So those are integers. And the metric of the vector parts is given also in terms of this pre-potential. But since this action is clearly gauge invariant, and the action we obtained before was not, so we don't expect the classical reduction to be put in this form. But it's interesting to at least to nevertheless try to do it. And if one can close to it by defining the following coordinates. So one defines the canonical coordinates in terms of the one you obtain from the circle reduction. And by defining this, the following pre-potential, you can write the action in this form. But this potential is not cubic. Well, the first part is cubic and gives rise to the gauge invariant Chern-Simons terms. The second part is not cubic and gives rise to this non-gauge invariant Chern-Simons terms. But it's still homogeneous of the grid. And as I said, this piece is related to the Green-Schwarz mechanism and is expected to disappear at one loop. So let's now turn to this one loop computations. So we want to compute quantum corrections to the Chern-Simons action in 5D. So Chern-Simons in 5D are induced by this triangle diagram, wherein the loop can run fermions and tensors. For a single spin 1/2 fermion of mass m and charge q, this result is very well known and is the following contribution. The coefficient is proportional to the cube of the charge and the sign of the mass of the fermion. Then the similar contributions can be obtained for the spin 3/2 and tensor running in the loop. This is done in this paper. And in our case, one has to distinguish two different cases. One where all the external gauge field are U1 gauge field coming from 6D, so these AIs. Then only the charge hyperines are charged under those, and so only those can run in the loop. But if all the external gauge fields are copies of the KK photon, then all the KK modes of all the spin 1/2, spin 3/2, and tensor fields are charged under them, so they can run in the loop. So this is a bit of a technicality, but one has to be careful about the external gauge field and what can run in the loop. So doing this, so putting all this together, we can find the full one loop corrected Chern-Simons action. So here I omit the wedges between the A and the F, just for otherwise it doesn't fit on the slice. And it might look messy, but because there is a lot of indices, but only these indices, for instance, the IJK denote the U1 coming from 6D. So here you have Chern-Simons term with 3 U1 coming from 6D. Here 2 U1s coming from 6D and 1 graviphoton. Here 1 and 2, and here only KK photons. And the Ks are the Chern-Simons coefficients, which are given by this term. So you see the cube of the charge and the sign of the mass of the fermion running in the loop. And here M is the charge of the KK photon. And then we sum over all KK modes that run in the loop. So this sum over N's include all KK modes running in the loop. But these sums are ill-defined, so we need to regularize them. And the often used regularization in the literature is the zeta function one, and it gives you a finite result. So here is the finite result displayed. This SI are some integer function, but you see that in every coefficient there is some piece that depends continuously on the VEF of these zetas. So those are the Coulomb branch parameter. And because it depends continuously on this VEF, which can take any real value, this is not properly quantized. So the case needs to be properly quantized in order the theory to be invariant under large gauge transformation in 5D. So this theory is problematic, and you see that each term which is problematic is proportional to the force power of the charge. So this is reminiscent of the anomaly that we started from an anomaly. So it's because we summed over all KK modes that this can happen. But this is not good, because this result is not enough, because it's actually invariant under small gauge transformation in 5D and shifts of the scalar like this. And this should not be the case. If you remember our small devil that said that evil should be concept. So in 6D, the theory was not invariant under this transformation. Well, this corresponds to small gauge transformation in 6D, and this corresponds to large gauge transformation on the circle in 6D. And the theory was not invariant under both. So something went wrong, and where it went wrong is the regularization, because we use this zeta function regularization. And in fact, the regularization should be something taking place in the UV. The divergent mode in these diagrams are the one with very high momenta, so in the UV. And in our case, this is not any 5-dimensional theory, but it's one coming from 6 dimensions. So that in the UV, it's one should preserve 6-dimensional Lorentz invariance. So if you look at the theory at length scales, which are much smaller than the inverse radius, then much smaller than the radius, then the theory is 6-dimensional. You cannot distinguish from it. So one should go ahead and look for regularization that preserves 6D Lorentz invariance. And one way to do so is to, for instance, start from a 6D polyvirial regulators and reduce it on the circle. So if you do this, you get a similar result to this one, but slightly different. It's also a finite result. But notice that there is not the VEV anymore on the scalars. It's the full field that appears in the coefficient. And the coefficient have been changed. I highlighted in red one that have been changed. And these two changes are precisely what is needed to make the reaction varies as expected under small gauge transformation and shifts of the scalar. So in that sense, the anomaly is preserved under circle reduction, and our little devil is happy. Furthermore, all these Chern-Simons terms which now depends on the scalar field, so they are field dependent. So these three guys combine precisely with the one we obtained from the classical reduction from the Green-Schwarz term. So they combine in this way, and so they cancel if the anomaly cancellation condition is satisfied. So if we started from a theory with no anomaly in 60, and in that case you find no field dependent Chern-Simons terms in 5D, and the theory is gauge invariant. So this is really making precise the slogan, the anomaly should be preserved under circle reduction. Very good. So now if we started from a theory which cancel all anomalies, not just the pure gauge, but all the other anomalies, then all the Chern-Simons action at one loop can be written in this form. And notice that this is all there is because it does not receive further correction beyond one loop. And this theory is gauge invariant and can be obtained from a usual cubic pre-potential, which is displayed here. And this is the fully corrected quantum corrected pre-potential. From this potential, you can read the corrections to the coordinates that I displayed earlier. So all the correction is included in this the function delta. And as a bonus, because supersymmetry relates for us the Chern-Simons terms and the kinetic terms, and we computed the corrections to the Chern-Simons terms, we can infer the correction to the kinetic terms. So here is the kinetic terms before correction, and here are the kinetic terms. They inferred corrections to the kinetic terms. Again, notice that everything is included in this function delta. And so now let me switch gears and talk about the implication this has for the effective theory, the 6D effective theories you can obtain from F theory on a Calabi-Yau threefold. So F theory on a Calabi-Yau threefold has 1,0 supersymmetry. That's why we looked at 1,0 theories. So in order to obtain this effective action, one uses the M theory duality. So you start from M theory, you compactify it on the Calabi-Yau threefold, you obtain as 5D theory which has n equal 1, and shrinking the fiber to 0, then this lifts for you to 6D. Well, in practice, how this is done is to start from any 6D, a generic 6D 1,0 theory, reduce it on a circle, and compare the so obtained 5D theory to the one obtained from the M theory reduction. Here it's worth noticing that the two 5D theories you obtain from reduction are very different in nature. This one is obtained by the classical reduction of the M theory on the Calabi-Yau threefold, while on the circle reduction side, you have to fully quantum corrected it. And this we just did in the previous section, at least for Abel and Geschwind. And now we want to do this to this side and then compare the two. And we will focus on the vector side. So the vectors in 5D coming from M theory come from the expanding the M theory tree form along with harmonic 114, which I denote omega. So of the AI, which are the 5D vectors. And the Chern-Simons terms you obtain in 5D from M theory come from the 11-dimensional Chern-Simons terms, which are given here. And the Chern-Simons coefficient you obtain are directly given by the intersection numbers of this 114, or equivalently of the Poincaré dual divisors, Ti. So, well, by Poincaré duality, every vector can be also associated to a Poincaré dual divisor. Very good. So in M theory, I just said that the Chern-Simons you obtain are just given by these intersection numbers. And these are just numbers. They are not field dependent or anything. And we just saw that if you had field independent Chern-Simons terms, this could only arise from the reduction of a theory which was anomaly free. If you had an anomaly in 6D, then this after circular reduction, you get some field dependent Chern-Simons terms. And because in M theory there is no such field dependent Chern-Simons terms, then the effective theory from F theory in 6D is also automatically free. So if you can use this duality. So that's one thing. Now we want to so this is one data one can say about by just comparing this at these two theories. What one might want to go further and to match every term, and this is actually possible due to supersymmetry, the fact that we can express, at least for the vector part, express everything in terms of this pre-potential. So let's go ahead and do it. so now we want to specialize to some Calabi threefold, which matches with our. 5 minutes.
You have three more minutes. Sorry, I forgot to say.
It's okay. It's okay. 3 minutes is perfect. So let's specialize to a Calabio threefold, which match with our circle reduction of a 6D theory, which has only abelian gauge field. So we take a Calabio with only extra section and which is smooth, so we don't have non-abelian gauge field. And this is a setup that has already been studied in the literature. And the correct basis of divisors for our vectors is the following. So the vectors AI, which come from the two forms in 6D, are given by these vertical divisors. The KK photon A0 comes from this the zero section, shifted in the following way. And the U1 vectors come from the extra section sigma I, shifted in the following way. So these 3Ds are the correct basis to shift to lift to 6D. And the M theory P-potential is given again in terms of this intersection number. So this is just a Chern-Simons coefficient. And this phi are the M theory coordinates, which are related to the Kähler coordinates obtained by expanding the Kähler form. So now you can compute the intersection number in this basis I just gave, and you find the following P-potential coming from M theory, so the classical. And this has to be matched, as I said, to the fully quantum corrected P-potential you obtain on the circle reduction. So let me just mention that here this product is made with the intersection matrix on the base, that this pi is the projection on the base. And that's the case are the coefficient of the expansion of the anti-canonic class on the base. So now we want to match this P-potential with the one we obtained in the previous section, which I display here again for convenience. And one find that they precisely match if one identify the M theory coordinates with the circle reduction coordinates and the matrix in the canonical way. If one identifies the Green-Schwarz coefficients in this way and the triple intersection number in this way. And these three identifications were already known in the literature. So this agree perfectly. And this is also a priori justification for our weird choice of coordinate we did in the beginning. So the anomaly matching leaves no space for you to choose anything. So this is completely fixed. And the match is only possible if all anomaly cancel. So the pure gauge anomaly is obvious, because otherwise you would have here some terms which are not cubic, but also the other ones in order to match with the M theory P-potential, and also if you use the adequate regularization, as I already mentioned. So this brings me to my summary slide. So let me. So I still have 1 minute now. Let me go through it. So we studied 6D anomalies on a circle, and we saw that if one uses a regularization that preserves 6D Lorentz invariance, it appears as field-dependent Chern-Simons terms in 5D. And those disappear, so are not present, when the anomalies are cancelled, which requires a Green-Schwarz mechanism in 6D. Then for anomaly-free theory, we obtained the full corrected cubic P-potential, from which we could read off the correct quantum corrections to the kinetic terms as well. And we saw that this had implication for F theory, namely that the AFTs of F theory are automatically anomaly-free. And we could match precisely the two P-potential from the M theory and circle reduction. In that case, when all anomalies are cancelled and one uses the adequate regularization. And this justifies the correct identification of the coordinates. Okay, thank you very much for your attention.
Thank you. Thank you for the very nice talk. Let me also thank virtually, like Fernando did. So, any questions for Pierre? While people are thinking of questions, maybe I can ask a quick question. So could you possibly comment on the non-abelian gauge algebras and also possibly non-supersymmetry cases?
Yes, so the non-abelian gauge algebra, I would say, so I didn't consider it for simplicity because then you would have more, so you would have the gauge boson, which are also, well, you would have fields in the gauge, in the vector multiplets, which are also charged under the algebra, which have to be considered in the loop. So it just makes the computation more tricky. But in principle, it would work exactly the same. So if it's so for the anomaly, you can read off from the Feynman diagram. It should work exactly the same. Then you could have global anomalies of this gauge group, and then this would be probably more tricky. So like if you're thinking of the SU2 with an anomaly, well, this is, but such anomalies would be more tricky. So I think this is clearly something to investigate more when you have more like global anomalies. But for the local anomalies, even if it's non-abelian, I think it works exactly the same. It's just the computation is more involved. And then if you have less supersymmetry, I don't think the argument relies on supersymmetry. So I think that, well, actually, in the first part of, so if you look at our paper with Diego in 4D, the first part of the paper is not at all relying on supersymmetry. So here in 6D, I went directly to the supersymmetry case to make it more transparent with the F-theory case, but it holds completely independent of supersymmetry. I would say that even supersymmetry forces you to be more careful that your regulator also preserves 6D supersymmetry, which is the case here because we started from a polyvector once, but if anything, it puts more constraints in this case.
Okay, thank you. Any questions from the audience?
I have a question. Can you say a little more about the relation between the two Calabi-Yau threefolds in this picture, the Y3 and Y3 check? Are they the same, or are they mirrors, or is there any known relation?
No, so the check one is the one is when you resolve it. If you have, so if F-theory can be defined on singular Calabi-Yaus, which are the singular, at the singularity, you have the non-abelian gauge algebra appearing. And so this check is just to indicate that you have to resolve it to be able to do the M-theory reduction, and then the blow-up divisor are the one which are going to give you the non-abelian gauge boson. But in our case, we just consider abelian gauge algebra in 6D. So we take Y3 to be exactly smooth. So in this case, they are completely equal.
I see.
So the abelian gauge theory come from extra section, which are not. So this in my case, they are completely equal. But in general, it's just a blow up of this Calabi-Yau threefold.
Okay, that's helpful. Thank you.
Any other questions? If no more, then let's thank Pierre once again. And then we move on to the next speaker, Peter. It must be a very late night there, right?
I'm not sure whether it's late or early. So I don't know if that answers your question.
Okay. So what's the 5 a.m. is it?
Yeah, 5 a.m.
So if you could start sharing.
Sure.
Could you make it bigger? Yeah, you're doing.
Can you see okay?
Yes. So our next speaker and the final one is Peter Merckx, who will join IBS-CTPU very soon. He will tell us about fine and coarse structures in the SDFT landscape. Please.
Thank you. And thank you for the invitation to speak. Before I move forward, let me point out that I've brought you here an image of a Calabi-Yau in the wild I believe in a shopping mall somewhere in California. And what I'll talk about is really a combination of a couple of projects in the hopes of relating some of the 60 SCFT story to the theme of this workshop, the Swampland and string landscapes. So we've seen variations on this picture a number of times so far, and not being far on the gravity side of things, I'll try to refrain from saying more about stronger criteria like the weak gravity conjecture that we've heard a lot about, and some other criteria that I don't know how much I'll have a chance to say about, but things including gauge algebra rank restrictions that come when we work over when we work requiring that we have a compact clavio in play. Okay, so the basic idea is that there's many effective field theories, and we can ask if we can couple them to gravity. And as we've seen, landscape consists of those things that we can couple to gravity, or in other words, have some higher energy limit that makes sense in string theory, and those that don't, we consider part of the swampland. And what I'll try to motivate any relation that may be visible to me in terms of is this very simple condition that we've heard mentioned several times that has been around in literature for a long time. For example, Banks and Seiberg do an excellent job detailing various features of this condition that any EFT in the landscape cannot have global symmetries, or at least the exact continuous global symmetries. And that may not be a sufficient condition, but it's certainly necessary, at least by the arguments that I think are generally accepted. Okay, so so part of the long-term goal here, I think that many are after, is really making sense of the 4D theories, but there are some difficulties in looking at the landscape of 4D theories that we don't face in 60, partly due to the simple algebraic geometry ingredients in the 60 case. So some of the subtleties I want to point out are that if we compactify from a 60 to a 4D SCFT, if we start with a 60 SCFT and compactify in a torus to get a 4D SCFT, other ingredients enter the story, and this allows, for example, in Howardson and others' work, this well-known quadrillion standard models case, one to beef up a small number of 60 SCFTs with additional structures that appear in 4D to reach a very large number of theories, 10 to the 15 of them at least, that are compatible with low energy limit that looks like the standard model. Okay, so in other words, we can't classify 4D theories easily right now, and it doesn't look like anytime soon that we will be able to. But we can take steps in that direction, and I think one hopeful set of insights in that direction would be to make better sense of what's going on in the 60 case. And since we have nearly complete classifications of 1-0 and 2-0 theories in 6D, one of the major steps in that direction coming from 2015 work of Heckman, Morrison, Hrdelius, and Boffa, and then some less sweeping follow-ups by myself, and then shortly after by Lakshya Bhardwaj. The goal here, I think, really is in my talk just to say a little bit about what the SCFT landscape in 60 looks like, and to point at some ingredients there that we might expect to carry over to some part of the structure that we should be hoping to see in 4D. Having spent a lot of my energy trying to make sense of global symmetries of these 60 theories, I think that one program that's related to this that looks like there's still room for improvement is to map out the set of 60 theories that have no global symmetries, and to map out which of those we expect to also have no global symmetries in 4D under various approaches to compactify from 60 to 4D. Okay, so the basic outline is just to say something about 60 SCFT models in F3 and then talk about their global symmetries and then sort of zoom out at a sort of more core structure level and try to say what the global, what the big picture core structure of 60 SCFTs looks like. And then to talk about a few insights that have appeared in the last couple of years in that sort of core structure that we see that we might expect to have some counterpart among the 40 theories. Okay, so the basic geometric preliminaries here that I think are worth a bit of time are to say that we want to start with an elliptically fibered Calabi-Yau, and indeed we could consider other Calabi-Yau threefolds to compactify on so that we get a 60 SCFT from F theory. But doing that really takes us to infinite distance and moduli space, and I think there's some open questions in algebraic geometry there that make a complete description in infinite distance difficult, although recent work understanding Rosen theories may be an important part of that story. So the basic picture here is we take a Weierstrass equation where the coordinates x and y tell us how to move around the preimage of a point in the base downstairs B that's a complex two-dimensional variety. And for our purposes, locally, this just looks like C2 and has, at worst, orbifold singularities. And this fibration by tori is non-singular. We have a bona fide torus upstairs everywhere except over the discriminant locus where a certain combination of F and G vanish that we'll see shortly. And while this may be a phrase in algebraic geometry language formally, I think it's worth making an invitation to people outside of this area and trying to give enough detail here to say that really we can do all of this work, which is sort of a surprise actually, that all this work really can be carried out without reference to hypermultiply counting and richer goals from anomaly cancellation, and really just by factoring these two variable polynomials f and g that tell us the nature of the singular fibers wherever they appear over the discriminant locus. So work from the 50s and 60s by Kadara and Tate tells us which type of singular fibers can occur, what sort of pinchings of tori can happen in other words. And I've listed here the usual F theory slide for trying to detail these singularities. Kadara's early work treated this singularity type as something of an artifact in algebraic geometry that really did not carry algebra content. It was just to denote a chain of -2 curves that had the appropriate Dinkin diagram shape. Later work in the 90s, decades after work by Kadara and Tate, with Tate's work refining the sorts of covers that we need in this situation, the sort of monodromies that can occur, was able to actually link these to bona fide physical theories. And so this final column that we see gauge algebras appearing was really not visible in this early algebraic geometry work that was geared at number theory. Okay, so the precise algebra that we find requires actually factorizing some monodromy cover, and in some cases this is quite difficult, and actually I'd say a good chunk of work in this area in trying to reach these classifications, at least in the 60 case, comes from trying to make sense of the monodromy cover in this I0 star case. Factoring cubics is generally quite difficult in two variables, and there's no well-prescribed algorithms that work for our purposes, so it's sort of a tricky bit of math to actually do this in all the relevant cases. And we have a similar dictionary for non-compact components of the discriminant locus, where our fibers, or which our singular fibers occur. And I'll say a bit more about this as we move forward. There's something I should point out, though, that these non-compact components will lead to a prescription for our global symmetry algebras. And there's a caveat that we need to run RG flow in this construction in both the gauge and global symmetry cases to actually reach a conformal theory. And we'll be making a model that is a bit too high in the UV without that conformality. And so if we want an on-the-nose classification in all cases where we can exactly read the algebra we expect in 6D, then there is some subtlety about RG flow that has to enter the story. Okay, so, but there are concrete things we can say, for example, that we expect any algebra we can construct to act on the Golem branch, and so we can sort of tell which algebras are bigger or smaller than expected. Okay, so the base case in trying to run this project is just to take a single compact component of the discriminant locus in this 4 real dimensional or 2 complex dimensional base. And this program I ran with Marco Bertolini and Dave Morrison several years ago, and it turns out that this is entirely treatable by elementary means without reference to anomaly cancellation directly and hypermultiplet counting. And I'll try to run you through this briefly since it's not really part of what I'm trying to get to in the long run today. So the idea is we take a single curve with the gauge algebra content that we read using the above tables, and we ask which intersections are compatible with this without breaking certain conditions that prevent a Clavier resolution from the orders of vanishing of the appropriate polynomials in the sense of the table above, at these intersection points. And we only have so many degrees of freedom along this curve, and so we can walk through and try to address every possible case. There are finite in many cases. And then we just ask ourselves, what are the maximal algebras that can occur on these compact curves? So in other words, you hand me gauged theory, you tell me it's gauge algebra and how it's constructed along this curve. And then I can ask what the global symmetries are on these non-compact curves that meet the curve that is giving rise to our simple gauge summand or simple non-abelian gauge summand. So the program outlined, I think, originally by Whitman and made more clear perhaps in other work, was essentially to we smoothly contract this curve in the base that holds the gauge algebra while allowing these other curves to effectively reach infinite size and lead to global symmetry algebras. There are some subtleties here, but I think in the interest of time, let's accept that that picture makes some sense up to issues of RG flow. There are some technicalities like these intersections have to be transverse. And if we want to understand this picture in the compact case where we might be interested in trying to actually tease out which theories can couple to gravities successfully, then we need to worry that our base should be compact and additional restrictions enter. And some of those restrictions include allowing transverse intersections, non-transverse intersections, tangencies. Okay, so how does this actually look in practice? I said we can do this by factoring polynomials. So let's take a look at a baby example. We take a Kodaira type 4 curve that corresponds to a gauge summand that looks like an SU2 or an SU3 depending on monodromy. Let's assume that the monodromy cover is actually split so that we get an SU3 summand. And then our general form of this FG and delta that we see where delta is 4 f cubed plus 27 g squared, over which its zero set is where we see these singular fibers. This is really quite simple, and we can ask how the vanishings on a transverse curve look from an intersection with one of these curves. And we can, in other words, see that f should vanish order 1 and g should vanish order 2 and delta should vanish, 1, 1, and 2 for fg and delta orders of vanishing. And now we ask what happens when we consider this monodromy condition before we had ignored this in writing this 1, 1, 2. And in fact, this tells you that a transverse curve intersecting this type 4 curve will have restrictions on the allowed degrees of freedom. And actually, I think I've flipped the intersections here. Really, I want this compact curve to be, if I'm saying that I'm worried about intersection contributions on the neighboring curve, I should be saying that this is really non-compact curve that is contributing some global symmetry. Anyway, so this simple counting arguments and simple factorization games suffices actually. And not only does it suffice in the 1D case that we treated Marco Bertolini and Dave Morris and I, but it works in the general case to classify at least the geometrically realizable global symmetries of all 6 DSCFTs, to at least those that are known to have an F3 realization. I should point out that that nice example we just looked at is not really the general type of story. Some cases are very difficult. And for example, a Kodaira type I6 curve with an SU6 or SP3 gauge summon has this as its general form. And there's a little gap, possibly not of significance for I7, I8, and I9. But of the infinitely many Kodaira types that are out there, there's really only 3 cases where there's any gap in sight. And I think there's not too much doubt that at least in the I7 and I9 cases that the gap can be closed. So I won't try to beat this case down, but I think it's worth just noting that a detailed inspection of orders of vanishing is required, but it's not too bad. And having looked at every single pair intersection of every possible set of Kodaira types, I can say it's actually quite elementary and straightforward to do in a short time. Okay, so what you get when you carry out this program is for every possible simple gauge algebra that can arise, you can write down explicitly what the maximal global symmetry algebras are. And the problem in physics is that we expect that there should be a unique global symmetry algebra. There should be a single maximum here, and that should be the global symmetry algebra of this theory. We see multiple algebras, and this is somewhat mysterious even now, but it should either correspond to some kind of hint that there is a collapse, say in this case, of these 3 algebras into some smaller algebra living within the field theoretic predictions for the global symmetry algebras here that takes place when we run our G-flow. Or this encodes that there are actually 3 distinct gauge theories here. So it could be that there needs to be a somewhat dramatic expansion of the classification of 6 DSCFTs with that expansion being encoded by the multiple global symmetry maxima we see, or there should be some insight about RG flow that resolves this multiplication of the set of global symmetry algebras we expect. So we can write them all down. This is them. We can also do the same thing when there's no non-abelian gauge algebra. This was done by Morrison and Reales shortly after. And we put those 2 things together. First, let me point out that predictions from field theory are consistent with this. So we can write down the representation theory content that we expect for each possible simple gauge summon, at least when we have a non-abelian gauge summon. And then we can write down from anomaly cancellation what we expect for the global symmetry algebras here. And indeed, we always find a global symmetry algebra that is geometrically realizable using the construction that I pointed to above with shrinking the compact curves in the base inside of this sort of bigger field theoretic prediction. So in other words, the field theoretic predictions for these algebras are weaker than the geometric constructions. Okay, so in moving forward, I want to point out that there is also the possibility that there are frozen divisors running around, in other words, orientable 07 plus planes. I'll try to exclude these from our discussion. I may try to say something at the end about how these play in the game. But I just want to look at the general case now. We've talked about what happens if you have a simple non-abelian gauge algebra in your theory. What happens if you have more than a 1D Coulomb branch? You then have several gauged compact curves in the base, and you can ask if there is any freedom for transverse intersection with non-compact curves carrying algebras that will become global symmetry summons. And so the same program in principle works. There should be really no difficulty believing that the same methods will go through with the sum of the transverse curves leading to the global symmetry algebra. But the difficulty is actually in doing this. It is doable, but it is not easy to do by hand, so computers get involved very quickly. The basic outline for what classification we're trying to treat is that we have some tree of curves. In this case, I've drawn just a chain of curves. So in this case, 5 curves that are compact. And I want to know every possible collection of transverse curves that is allowed to intersect these. And so we go through and enumerate by brute force those transverse curves with some computer algebra help. And one can do this. To give you a sense of what kind of breadth we have to treat, the sets of curves, if I just list their self-intersections, are here at least for clusters that can glue to other clusters. And so sort of the inner ingredients, the pieces of the chemistry of the 60 SCFT classification that we should be worried about are these inner pieces, because they're very constrained when they glue to sort of larger molecules that hold larger gauge summons, and sort of perhaps an overextended metaphor to chemistry. So essentially, when a curve has negative self-intersection of 4, 5, 6, 7, 8, 9, 10, 11, 12, then we may or may not be able to glue some of these links, we call them, to one of these nodes. And so in this picture, for example, one base we can read as sort of a pair of nodes glued between some links. And this language of nodes and links comes from this work of Heckman, Morrison, Rodelius, and Boffa from 2015, the atomic classification of 60 SCFTs. There was a few theories that were able to be trimmed based on early work.
You've got 5 more minutes to say.
Cool. So we were able to throw a couple of links away, actually really only branching links that had some defects, and then a few families of theories got tossed due to some constraints that are not visible until you dive deeper into the geometry. They don't have any problem with anomaly cancellation. Okay, so we can actually write down all the gauge algebras for those links, and since everything glues to them, they really are the moving pieces. So there was an initial attempt to do this. There was some trimming of this list in revisiting this classification geometrically. But every gauge algebra for the sort of moving pieces of the classification can be smacked on a page in ultra small font, as you can see. And so here's the picture for what we're trying to attack as a problem with our computer to write down all global symmetry algebras in the hope of searching for SCFTs, perhaps that don't have any global symmetry algebras, or at least that meet a restriction that when we compactify to 4D and run RG float, we'll lose those global symmetry algebras. So we can search through the space of 4D SCFTs for those that are at least potentially outside of the Swampland or in the landscape. So the real question here is, how do you compare huge lists of semi-simple algebras and then find which ones are relatively maximal? And then how do you find out which collections of curves are consistent with a Calabi-Yau threefold? In other words, don't have too severe of a singularity somewhere to allow a Calabi-Yau resolution. The answer is just brute force computer programming. So I'll spare you the details. There's some by hands work to make sense of the intersections, doing some factorizations of 2 variable polynomials, but it's fairly straightforward. Okay, so zooming out, and now that we've seen the sort of nitty gritty at its finest detail, and I hope it imparted some kind of sense of what the breadth of the classification is and alleviated fears about working with it directly. I'd like to talk about the orbifold bases that arise that group together families of these 60 SCFTs. Each base that we saw over which we have these elliptic fibers is really just an orbifold that we can think of as C2 mod a discrete subgroup of U2. And not every discrete U2 subgroup appears. And actually this is somewhat mysterious. So really one of the key questions here is, why do we see the U2 subgroups that we see? Every discrete SU2 subgroup does appear, and these have been classified, and this helps provide realistic checks that the classification is at least somewhat sensible and complete. And So the idea is you give me a base that's this list of numbers, and there's some branching allowed in these bases, but again, in that case, the same will apply. So we'll just iteratively blow down all the -1 curves in the base. For example, here we blow down first this -1 curve on the left, and we end up reducing the neighboring -3 curve, and it becomes the -2 curve. And we repeat, eventually we end up with this endpoint, just the -2 curve. So we can ask which endpoints are there. And it turns out that one can characterize this set of endpoints just by telling me a list of rational numbers that I'll try to write down more about in a minute. So these rational numbers come in families. So it's not just that endpoints give you families of SCFTs, the endpoints themselves come in families. And when you ask what the properties are of this sort of set of all endpoint families, then you've really zoomed out very far from the structure of studying gauge content of a single SCFT. So let's see what we can get with this sort of bird's eye view structure. So I should say that these rational functions have purely integer coefficients. N here just indexes a height in a skyscraper that we can think of starting at height 0. And then every 60 SCFT appearing in an F-theory realization, at least those that are known, excluding frozen divisor cases, then is captured by one of finitely many of these fractions with some choice of the integer n. Those were classified by Heckman, Morrison, and Boffa, and some further insights were provided by follow-up work by Morrison and Boffa. So what's the action here on C2? It's the usual orbifold action. We rotate first and second coordinate by some multiple. And this is the same underlying mathematics of this Hertzberg-Jung continued fraction story of the surface quotient singularities. So in other words, we go from a rational number to an entire set of SCFTs, and we go from families of rational numbers from one of those linear, or one of those meromorphic functions, this linear rational function, to families of these rationals. And so one can ask, what is the structure of this? And I think this was not initially apparent even once every SCFT endpoint was classified and fit into this structure. There's a few subtleties here that may be relevant to this Swampland picture. At large n, these gauge algebra ranks, they grow as you increase n, and you really need some constraints on the rank of algebras that appear if you want things to couple to gravity. I think this is part of the picture that maybe is relevant to consider what the small n structure is here. And the other part of the story I think that's relevant is that if you compactify to 4D, you don't expect this huge stack of family structures to completely disappear. So hopefully some further understanding of what's going on in the 6D case could help us out in the long run. Okay, so the cartoon picture here is you only have really 78 linear endpoints, and there's 3 branching endpoint families, 78 endpoint families, I should say. Okay, so within them, each has infinitely many endpoints. So these families look like a chain of 2s and a 3, and a chain of 2s and a 3, 2, and this list goes on. There's 78 legitimate families of these. Why 78? Well, it's 144, but you don't care about reflections, and it's really a 12 by 12 grid where you don't care about the ordering, and so you end up with 78. Okay, so within each family, there's endpoints, and within each endpoint, there's these bases that blow down to endpoints. And once you fix one of these chains of curves, I can then decorate the curves that I see here with various algebra summons. And what this tower of theories really looks like through in the sense of sort of various notions in discrete math is largely unclear. But there is a sort of unifying picture. Every one of these linear endpoint families, and actually even the branching endpoint families, turn out to fall within the linear endpoint families in a certain sense that the determining rational numbers are exactly the same as a rational number from a linear family. Every one of these falls as some infinite truncation of this long E8 chain, where the E8 gauge summons live on these -12 curves, and there's a unique link that can allow them to glue together at large length. So to conclude, I just want to say that there's some additional structure here. In recent work from 2019, I just looked at this question of what happens when you take n to be very small. Can you make n negative? And I think it was not really understood that there was some subtlety in the way that we treat negative values of n, that there has to be some by-hands correction to do that. But it turns out that if you do that, you really get a reflection of the tower of all SCFTs. You get a sort of mirror image below ground. And this mirror image is actually not a direct reflection. It somehow permutes and swaps the various families of endpoints. And interestingly, there's more structure there. And if one probes the structure directly, that swap of families turns out to be a distinguished order 2 map on this set of endpoints that respects their inner structure. It respects not only the endpoint families, but the endpoints. And furthermore, it respects the SCFT structure within each endpoint. Concurrent work by Heckman and Ridelius found that there's a beautiful story about nilpotent orbits in E8 that makes good sense of part of this. If we look at this on the previous slide, this chain, this distinguished chain of unique bases that lives within each endpoint, from which you can reach every endpoint by truncating on the left or on the right and then blowing down all the curves, you find that there's a natural way to build nearest neighbor theories. And this is a simple picture of this. It's sort of hard to see that it's actually symmetric. It's really a 3D, it only naturally embeds in 3D, this graph, but it has 24 automorphisms. And one of the distinguished order 2 automorphisms is this level inversion, which really, to make decent sense of how that goes, requires some care in working with the underlying orbifolds. And I want to point out that in algebraic geometry, the orbifold—
Peter, just to say, we are running out of time almost, so.
Okay, yeah, just 1 minute. This is the second to last slide.
Okay.
So what's really going on in an exchange of endpoints that we're seeing, this sort of level negation is the key ingredient to show us that this is a level preserving map, that the n is preserved in this exchange between endpoints. Further inspection, actually explicit computation of the gauge algebras in that exchange shows that their structure is preserved, that it appears that this actually exchanges sets of SCFTs. There's some difficulty in making sense of this full in the nilpotent orbit story. But I think just having some sort of clear picture that there's some simple structure underneath the set of all 60 SCFTs maybe gives us hope that the same structures will carry over in some form to the 5D cases and maybe the nastier 4D cases. There's a number of mysteries here. There's some breakdown in that gauge algebra correspondence, at least in the explicit results that are available. And that suggests that maybe there's something, little tweaks to our classification that need to be made should we wish to actually attack our problem combinatorially and identify mathematical structures in combinatorics that show us what's happening here, or determine what this new structure is that we're finding, if it is in fact novel. There's a bit more subtlety here, but I'll move on. Okay, thank you.
Thank you. So thank you for the nice talk. As we are in fact running out of time, maybe we can get a one quick question for Peter, and then we transition to the discussion session. If there is any urgent question from the audience. If not, actually, I think it's maybe better to let the audience to think about the questions while we already jump to the discussion session. So let's thank the speaker once again. And then let's move to the informal discussions, where you can also ask to Peter, of course. So I will turn off my video. So anyone can ask anyone else even within the audience. So maybe I can start. Irene, are you there? Maybe I can ask you a quick question. Maybe you've already answered during your talk, but just to clarify. Oh, hi. So, so just to clarify, did you actually mean that? So there are two different types of strings you can imagine: weakly coupled or strongly coupled. And did you actually mean that there is always at least one weakly coupled one in the limit, or could it be that everything is strongly coupled?
No, exactly. So in the infinite distance limit, there is one weakly coupled. What happens is that if you take one which is strongly coupled and you study the back reaction and the energy flow, it's going to drive the scalars. I mean, you're not going to reach the infinite distance limit because you are going to leave the Keller cone before. So like they push you to the boundaries, and that's why they become tensionless at finite distance, like before reaching the infinite distance limit. So only the ones that are weakly coupled allow you to go to infinite distance, because then all the instances are suppressed along the entire flow. And that's why the correspondence between the infinite distance is only with the weakly coupled string. So for every infinite distance limit, you should have a weakly coupled string.
And then you said the uniqueness is not clear yet. Is that correct?
Yeah, I don't know. I mean, Fernando, do you have any comments on this? I don't know. I need to see if we can prove uniqueness.
Uniqueness. Well, about the other one, I mean, a strong coupled, we don't know what happens. No, it could be. I mean, we really don't know. The finite or infinite is classical statement. About uniqueness, you mean that there is always one which is lighter than the other, that they don't go tensionless in pairs? Is that the question or a different one? Sorry.
If there is always just one string that becomes light and not several strings that become light at the same rate, right? That's what you are answering in your works. I don't know.
In examples, that's what happens, no? I mean,
yeah, exactly.
We build the trajectory based on one charge, right? And that's the string that becomes tensionless. So in this sense, yeah, now some others are carried along.
So the thing is that, I mean, here we take the other approach, right? Like you choose some string, like some charges, and then you study what is the limit, no, that you are approaching. So in that sense, it seems that, I mean, for every charge that you choose, you get a different limit. But I don't know. I mean, I'm not sure if there is a way to approach the same limit, but from different trajectories, so that corresponds to different charges, and somehow then both become light there at the same rate. I don't know, I should think more about it, but I think that at least for the, like the elementary ones, like they are just charged under a single B field, then there is only one, because you choose a charge and then you get this infinite distance limit and that's it. But more complicated scenario, I don't know, it gets mixed with the trajectories and everything, so I don't know.
It would be very weird if there was some other string with another charge that becomes tensionless faster than this one, the one that by which we build the trajectory. It's very weird. We haven't seen it in many examples, but I don't know if one can show it in general. Yeah.
Well, it's also true you can take multiples of the charge.
Yeah, but
I guess that's where the complication starts, right? Because if it's just a multiple of the charge, it's gonna have the same scalar dependence. But then probably they are not stable. I don't know. I mean, that's interesting to understanding the microstates of these things.
Okay, but yeah, well, you have a cone of charges, but I think if you restrict the generators of the cone, then it's where we go. Okay, we don't know, but it doesn't. It looks like yes,
yeah.
But we don't know how to see it yet. We'll think about it. No?
Okay.
I have to say that everyone that wants to stay in the discussion should put their camera on or something. So it's easier to to make questions. Not forcing anyone.
Well, it's true. It makes for more lively discussions. I have to say, when you have office hours with a whole bunch of kids and they're all talking to you and you can't see any of them, it makes you think, wouldn't this be more productive? I mean, if they're all looking confused, you know to slow down, for example.
Maybe can I ask a quick question also to Alessandro, if you're around, just to.
Yes, of course.
Trying to turn on as many videos as possible.
Okay. Yeah. Very good. You spot me. I was here. I was listening.
So in the Minkow's case, so again back to my question during your talk. I guess in the Minkow's case, you would expect there is some sort of upper bound for the discrete symmetry order, and
yeah, it would be nice, right, to have so. Why you say there is an upper bound in what sense? In which sense? In what kind? Which one of the two conjectures are you talking
so I'm thinking about the first one actually here, because again, because this one was about large k, and then if there is some upper bound which is not too large, then I was wondering like how I could interpret this conjecture.
Well, okay, so you are saying that maybe if k is too large, then the coupling constant is going to 0, and then you have like a global symmetry, right? So you are breaking your no, I don't know. Wait, this is no, I
was more thinking of a sort of some possible upper bound from different perspective, and then if so, then what would this first conjecture possibly imply if you cannot increase the discrete symmetry order too much?
I think it makes sense not to assume that there is some upper bound for the discrete symmetries, for the rank of discrete symmetries in string theory. Yeah, I agree. I think I mean, probably in the end, that means that we can get some scale separation, but not parametrically large or something like this, no?
On the, yes, that's in the second conjecture, yes. Also in the first one, I think that there should be an upper bound also for the reasons that I was mentioned, right? No, at some point you maybe reach maybe at infinite. Well, of course, it will be if k is going to infinity, then it's like not more a discrete symmetry. It's like okay, but it would be nice to find an upper bound, right? It's like something that it's like finding an upper bound on the maximal rank of gauge theory that you can have in the continuous symmetry case. But of course, it should be able to to find also something in the case of the discrete symmetry would be nice. I don't know. I don't know what would be. Maybe Angel is here, maybe he knows. You can say more.
Well, I would say that the question is, where is this upper bound coming from?
Yeah.
In general, I can imagine that if the discrete symmetry is coming in some particular setup from brains or whatever, there could be tadpole constraints. But for instance, in the ADS examples that we had, there is no upper bound. You can take K as large as you want.
Yeah, that's true.
The only issue is that, as Alessandro was saying, the larger the K you take, the smaller sun gauge coupling is becoming. So that means that you're going to some point of extremely weak coupling, you're recovering a global symmetry. So probably that means that there will be some tower coming down, like in the distance conjecture, which is kind of spoiling your effective theory. Right. But it's not like a sharp bound on K. It's more like when you take K large, something bad happens.
Right.
About the sharp bound, it may be, I don't know. People have been looking for bounds on the order of discrete symmetries, but there is no clear argument why there should be a sharp bound, like saying it's lower than, I don't know, 2000 or whatever. I don't know.
But also, have you thought the relation with the sublattice with gravity? Because it really seems that this K might also be related to the order of the sublattice. So if it can be parametrically large, you will also get all these loopholes of the weak gravity conjecture and so on, that you can have a sublattice with a very large scale. No? So that would be problematic.
I haven't thought about it. I think there may be a relation, because at the end there is an issue of quantization of charges, but I haven't thought about it.
One sort of probably ill-informed comment is that in the RG flow story for the 60 theories, and there's a sort of related business of gauging, sort of promoting global symmetries. The gauge symmetries are working in reverse direction. There's this surprise that comes out in the classification once you actually have the global symmetries in hand explicitly and try to write them down, and you find that continuous degrees of freedom get lost in the 60 SDC case when you try to gauge the global symmetries. So if one is trying to do a search through the landscape for what will end up being landscape theories, then you should essentially, at least in the 6D case, and presumably in their reductions, unless something to do with fluxes complicates matters in 4D, then you should essentially have a finite list of groups to work through that have finite rank. And then fully gauging any global symmetries away when possible appears to give you a discrete group. And since they were compact groups to begin with, then I think you get finitely many. And so just working through the option, I mean, there should be a number that is the bound on the size of available discrete symmetries. But I don't have any way to give you that number. So. And I have no idea how U1 factors will play into the story either. So it could be much more complicated.
But Peter, you're saying that you can think of I mean, that it would make sense to have an upper bound on the setups that you study. I mean, coming from 6D to 4D. Okay. Because otherwise, so what's the argument again? So you would be gauging too many? What is the...
Well, I don't really know any way to get any kind of sense of what this bound should be, except that they're going to have to fit inside compact groups. And you're going to have finitely many summations to begin with because of the continuous rank restrictions. And then when you gauge away any global symmetries, you should be left, except for U1 issues that I can't promise don't give you something complicated with something finite, barring some sort of, yeah, I mean, I don't see, if they're really discrete, I don't see any other way than, so you should have a number that is the largest number of discrete symmetries available to any 60 theory that's compatible with gravity. But I could be wrong. There may be some subtleties here. I have not thought about this before.
I mean, this question would be related to the highest charge, probably, right? So what the maximal charges that you can get, for example, in a abelian gauge theory,
right?
Because this would then give you the rank if you break the coarseness of the discrete symmetry, the K.
Yeah, that's why it's hard.
So, well, it looks like we are either running out of questions or are getting very tired. Maybe, but in any case, because our session was getting a bit long, maybe we could, at this point, close the session unless there are any further discussions or questions, maybe. Fernando, would you think otherwise?
I think it's a good time to close. Or getting up one more day.
It's very windy in your place. We can't hear you.
I'm sorry, I have Tramontana issues. It's for a while. So I repeat, yeah, I think a good time to thank all the speakers of today again, all the attendees, all the participants as well for joining us one more day, and maybe see you tomorrow.
Great.
Yes.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye. Bye-bye.
Thank you for hosting.
Bye.
Thank you. See you all.